GCE Advanced Level Chemistry Practical Series Experiment number 27. Tests for aldehydes and ketones. The aim of this experiment is to observe some characteristic reactions of aldehydes and ketones. Now students, in this experiment we are going to take aliphatic aldehydes and ketones and a set of aromatic aldehydes and ketones, and we are going to observe their solubility in water. We are going to observe how they react with some oxidizing agents such as acidified potassium permanganate, acidified potassium dichromate, and then we are going to move on to some specific reagents such as Fehling's solution and Tollens reagent, and observe how aldehydes and ketones react with these very specific chemical reagents. So let's dive into the introduction of aldehydes and ketones. Both aldehydes and ketones contain a carbonyl functional group. So that is the most important part to note when it comes to carbonyl compounds or aldehydes and ketones. They have the C double bonded O group. Now students, keep in mind even carboxylic acids contain a C double bonded oxygen group. However, that is not referred to as a carbonyl group. That is a specific separate functional group of its own called carboxylic acids. When it comes to carbonyl compounds, we only consider aldehydes and ketones, and both of them contain this group C double bonded to oxygen. Aldehydes and ketones differ in their reactions because, unlike ketones, aldehyde has at least one hydrogen atom attached to the carbonyl carbon. When it comes to aldehydes, there's at least one hydrogen atom connected to this carbonyl carbon. Therefore, structurally, aldehydes and ketones are different. So therefore, we can observe some different observations when we are reacting aldehydes and ketones with different chemicals. Aldehydes have at least one hydrogen attached to the carbonyl carbon. In ketones, no hydrogens are directly attached to the carbonyl carbon. Only carbon containing alkyl groups are present when it comes to ketones. So when it comes to aldehydes, you have this structure where you have R connected to the carbonyl carbon, and you have at least one hydrogen connected to the carbonyl carbon. So this group that we have here, is our carbonyl group. This is our carbonyl group. To the carbonyl carbon, you can see at least one hydrogen attached to it. When it comes to ketones, you have no hydrogens attached to the carbonyl carbon. You will have two alkyl groups attached to the carbonyl carbon. You wouldn't see any hydrogens attached to the carbonyl carbon. So this is the difference between aldehydes and ketones. What you have over here is an aldehyde, and this is your ketone. So when it comes to aldehydes and ketones, this is the structure difference that you observe. Physical properties. Due to these structural differences, they have different chemical reactions, but we are going to take a look at the physical properties of aldehydes and ketones in general. Boiling points of aldehydes and ketones are higher than those of alkanes of comparable relative molecular masses. So if you take alkanes that has a comparable relative molecular mass, and if you take an aldehyde or a ketone with a similar molecular mass and observe their boiling points, you would see aldehydes and ketones tend to have a higher boiling point compared to alkanes. This is because when it comes to alkanes, between alkane molecules, there are mainly van der Waals interactions or van der Waals forces or London forces. When it comes to aldehydes and ketones, however, we have dipole-dipole interactions. You will see when you're talking about aldehydes or ketones, they contain a carbonyl group. I'll draw an aldehyde for this particular example. You can see the carbon and oxygen, when they are connected through a bond, oxygen is extremely delta negative, one of the most delta negative elements that you find in the periodic table, and it will pull these bond electrons more towards itself, creating a partial negative charge, leaving the carbon here partially positive. So there's a charge distribution like this, or we can say polarization of the bond like this, which would lead to formation of a dipole, and therefore you will have dipole-dipole interactions between the molecules. So if you have another alkane molecule here, you will see, due to polarization of this carbon-oxygen double bond, there will be dipole-dipole interactions between the two. Now, this is considerably a strong type of interaction compared to London forces. Therefore, you will have higher boiling points in aldehydes and in ketones, because both aldehydes and ketones have this dipole, so therefore they can produce this dipole-dipole interaction. However, their boiling points are lower than alcohols of comparable relative molecular masses. Now, this is because alcohols have a OH group, which would lead to formation of a hydrogen bond. Compared to dipole-dipole interactions, hydrogen bonds are a bit stronger. So hydrogen bonds are a stronger type of intermolecular attractions. So therefore, since alcohols contain hydrogen bonds, right? So we can read through this sentence again. However, their boiling points are lower than alcohols of comparable relative molecular masses. And the reason for it is given right next to that particular statement. Alcohols form intermolecular hydrogen bonds. They form intermolecular hydrogen bonds, which are stronger intermolecular forces than intermolecular dipole-dipole interactions seen in aldehydes and ketones. So, compared to dipole-dipole interactions, hydrogen bonds are stronger. Compared to dipole-dipole interactions, hydrogen bonds are stronger. That is why alcohols of a comparable relative molecular mass to aldehydes or ketones have a higher boiling point. Aldehydes and ketones do not have hydrogen bonds between their molecules. However, if you dissolve an aldehyde or a ketone in water, with water, aldehydes and ketones can produce hydrogen bonds. So, aldehydes and ketones do tend to dissolve in water due to the formation of hydrogen bonds. But as the relative molecular mass of aldehydes and ketones increase, the alkyl groups or the size of the alkyl groups attached to the carbon-carbon increase. So these alkyl groups, they are hydrophobic. So as the alkyl group increases in size, the solubility of the aldehyde or the ketone in water will decrease. So what I'm trying to say here is, when it comes to aldehydes and ketones, only the aldehydes and ketones that contain relatively smaller molecular masses actually dissolve well in water. When you have aldehydes and ketones with relatively higher molecular masses, they don't necessarily dissolve well in water. Some are completely immiscible in water, especially aldehydes and ketones that contain an aromatic ring or benzene ring is not going to be soluble in water. As we know, we have a partial negative charge here and a partial positive charge here. And if you take a water molecule, water molecules contain on hydrogen partial positive and on oxygen partial negative charge, which could lead to formation of an intermolecular force between partial negative charge oxygen and hydrogen attached to an oxygen atom, which is a hydrogen bond. So what we have formed here is a hydrogen bond. We have formed a hydrogen bond. So due to formation of hydrogen bonds, aldehydes and ketones will dissolve in water. And what actually contributes to formation of these hydrogen bonds? Mainly which group contributes to formation of this hydrogen bond? This group. And this R group or the alkyl group is a hydrophobic group. So if the R group increases in size, which is a hydrophobic group, the solubility of the aldehyde, the solubility of the ketone for that matter, will decrease. So as long as you have a smaller alkyl group, or as long as you have a aldehyde or ketone which has smaller molecular mass, it will dissolve in water. If you are talking about aldehyde or a ketone which has larger molecular mass, it will not dissolve in water. Aldehydes and ketones can participate in intermolecular hydrogen bonding with water. Therefore, aldehydes and ketones with relatively lower molecular masses are soluble in water. Relatively low molecular masses are soluble in water. Now, some examples are given here. Water solubility of aldehydes and ketones. You can see if you take the smallest aldehyde that you can find, which is methanol, formaldehyde, or methanol. Methanol has a relative molecular mass of 30. It is miscible in water in any ratio. In any ratio. When it comes to ethanol or acetaldehyde, it has a relative molecular mass of 44, which is relatively small, which is also miscible in any ratio in water. Miscible in any ratio in water. However, if you move on to propanol, it has somewhat of a higher molecular mass. So, of 58. When it comes to water solubility, only 16 grams per 100 milliliters of water can be dissolved when it comes to propanol. If you try dissolving more of it, there will be layer separation. It will not necessarily dissolve in water. If you try dissolving more than 16 grams per 100 milliliters of water. So therefore, we can see there's a limit to the amount that we can dissolve when it comes to propanol. So as the number or relative molecular mass increase, the solubility of the aldehyde has started to decrease. If you look a step further, when it comes to butanol, only about 7 grams per 100 milliliters is soluble in water. So you can see the solubility is going down. And if you're talking about 2-propanone, which is acetone, it has a molecular mass of 58. It is miscible in any ratio. Now, up until this point, we looked at aldehydes. Now we are going to take a look at ketones. So ketone 58 is relatively a smaller molecular mass, as we saw here. When it comes to aldehydes also, in aldehyde, propanol, which had 58 molecular mass, was soluble in water up to a certain extent. when it comes to propanone or 2-propanone, it is actually miscible in water. When it comes to 2-butanone, it has 72 molecular mass, only 26 grams per 100 milliliters of water is soluble. But when you're talking about aromatic aldehydes and aromatic ketones, they are definitely insoluble in water. As soon as you introduce an aromatic ring or benzene ring into the aldehydes and the ketones, they are not going to be soluble in water because the benzene ring is a large hydrophobic structure. You will not be able to dissolve aldehydes or ketones that contain a benzene ring in water that easily. So therefore, they are going to be immiscible in water, not going to mix with water. So keeping that in mind, let's move on to the reactions of aldehydes and ketones. The carbonyl group is polar because of the electronegative oxygen atom attached to the carbon. So we know when it comes to carbonyl compounds, you have carbon-oxygen are connected through a double bond. Oxygen is a very electronegative atom, so therefore the bond will be polarized. Oxygen will be partially negative, whereas carbon is going to be partially positive. Hence, the carbon atom is electron deficient and can react with a nucleophile. So, what is the meaning of electronegative, students? Meaning of electronegativity is the what electronegative or when we say an atom is electronegative, what it means is there's an atom connected to another atom via a bond or through a bond. And when you're talking about carbon oxygen, since the oxygen is more electronegative, it has the capability of pulling the bond electrons more towards the oxygen atom. So electronegativity in summary means the ability that an atom has to pull the bond electrons more towards itself. So when the bond electrons pertaining to this carbon-oxygen double bond is pulled more towards oxygen atom, carbon atom is going to have lower electron density around it, making it look like an electron deficient region. So therefore, nucleophilic groups can start a reaction with the electron deficient carbon atom. So most of the reactions that we see pertaining to aldehydes and ketones are nucleophilic reactions. The carbon atom is unsaturated because it is attached to 3 atoms. It can therefore form a new bond with a nucleophile, right? Since there's a double bond, it is unsaturated. Carbon is connected to only 3 atoms. Don't mistake this for the number of bonds. Carbon actually has 4 bonds. However, since it is containing a double bond, carbon is attached to only 3 atoms. So carbon is unsaturated. So when a nucleophile comes its way, it can actually connect with the nucleophile and form a new bond there. During this process, the 2 pi electrons are transferred to the oxygen atom, thereby acquiring a negative charge. This negative charge is neutralized by attachment of a positively charged species, very often a proton. Therefore, the characteristic electron reactions of aldehydes and ketones are nucleophilic addition reactions. For example, if you take an aldehyde like this, and we'll take a nucleophilic group called X, right? So let's say there's a nucleophilic group called X like this. We know oxygen is partially negative, carbon is partially positive. Carbon is electron deficient at this point, or we can say there's low electron density around carbon. So therefore, nucleophilic groups can initiate an attack like this. We'll draw it in a different color so the electron transition is clearer. So this will produce a new bond between carbon and the nucleophile. And the oxygen will have a negative charge because 2 electrons were given to oxygen. Majority of the time, there will be protons in the medium, or a proton will be obtained from water, and this negative charge will be given to a proton, and you will see the formation of a neutral compound like this. What you can see here is the X nucleophile initiated an attack, and afterwards what you are left with is a neutral compound that has 4 different groups attached to it. When it comes to the aldehyde, it only had 3 different groups attached to the carbon and carbon. Now you can see 4 different groups attached to the carbon and carbon, which indicates this type of reaction is a nucleophilic addition reaction. So aldehydes and ketones normally take part in nucleophilic addition reactions. Right, let's move on to the next slide. Reactions with 2,4-DNP, which is Brady's reagent. 2,4-dinitrophenylhydrazine. In certain literature, you would find this abbreviation to be 2,4-DNPH. 2,4-DNP stands for 2,4-dinitrophenylhydrazine. Brady's reagent can be used to identify aldehydes and ketones. Now students, Brady's reagent can be used to identify carbonyl compounds separately from other organic compounds. So both aldehydes and ketones answer positively to Brady's reagent. You can't identify aldehydes from ketones or ketones from aldehydes with the use of Brady's reagent, because Brady's reagent actually is used to identify carbonyl compounds separately from other organic compounds. So if you have a mixture of, or if you have 2 samples of let's say an alcohol and an aldehyde, to identify the aldehyde you can actually use Brady's reagent, because alcohol will not answer to Brady's test or Brady's reagent. 2,4-dinitrophenylhydrazine, Brady's reagent, reacts with carbonyl compounds to form a yellow-orange color precipitate, or else it is referred to as a bright orange color precipitate. Preparation of Brady's reagent. Take a small mass of 2,4-dinitrophenylhydrazine and dissolve the solid by adding concentrated sulfuric acid and methanol. Now students, the methanol is used as a co-solvent here because certain aldehydes will not be soluble in an aqueous solution. So methanol aids in dissolving water-insoluble aldehydes and ketones in this solution so that we can get a more accurate result. The yellow-brown solution formed is Brady's reagent. Water can be added to dilute the solution formed. So when you mix these reagents together, you are going to obtain a yellow-brown color solution, which is our Brady's reagent. And if you want to dilute it a little bit further, you can do so by adding water. So you can see here how we have actually prepared Brady's reagent. We have the solid 2,4-dinitrophenylhydrazine. We take a small amount of that solid, dissolve it in concentrated sulfuric acid and water. We can add methanol as a co-solvent, and the yellow-brown solution that we are forming is going to be our Brady's reagent. So dissolve acetaldehyde and acetone in water and add a small amount of 2,4-dinitrophenyl or 2,4-DNP and observe any change. So if you take any aldehyde or any ketone and react it with 2,4-DNP, you are going to observe a yellow-orange or a bright orange color precipitate. You might observe the entire test tube turning orange, but keep in mind it's a very fine precipitate that is formed. So initial observation would be the entire thing turns orange, but if you let the precipitate particles settle for about a minute or two, you will see that this is in fact a precipitate that is formed. This is not a solution. So you can see here, when it comes to this reaction, the carbonyl group, the oxygen bonded to the carbonyl carbon, and the hydrogen on one of the nitrogens that is here will get removed as a water molecule. And this carbon double bond will actually get connected to the nitrogen, as you can see here. Instead of a carbon-oxygen double bond, now we have a carbon-nitrogen double bond formed here. And this is going to be your yellow-orange color precipitate that is going to be formed. Now, students, keep in mind, what we have here is ethanol. We have ethanol, and when ethanol reacts with 2,4-DNP, you will form a derivative of 2,4-DNP, which is ethanol 2,4-dinitrophenyl hydrazone. Earlier on, it was referred to as hydrazine, or 2,4-DNP was referred to as 2,4-dinitrophenyl hydrazine. But once this 2,4-dinitrophenyl hydrazine reacts with an aldehyde or a ketone, a derivative of this 2,4-dinitrophenyl hydrazine will be formed here. And that is going to be named, for this particular instance, since we reacted ethanol with 2,4-DNP, what we have formed here is ethanol 2,4-dinitrophenyl hydrazone. The name ends with ONE now. Earlier on, it was hydrazine, how the name ended. Now, it ends with hydrazone. So students, when it comes to each of these reactions, the derivative will be named like that. You can see the next compound that we have is 2-propanone, or we can say acetone. We have the propanone here. So when propanone reacts with 2,4-DNP, we are going to be forming a derivative which is propanone 2,4-dinitrophenyl hydrazone. It is important for you to know the structure of 2,4-DNP and how the reaction actually takes place. So let's take a look at what type of reaction actually takes place here. Now students, if you take a look at the nitrogen here, the nitrogen over here has a lone pair. So this lone pair of electrons can be donated to the carbon over here, which is slightly delta positive. Or we know when it comes to the carbonyl group is going to be polarized, where oxygen is slightly delta negative and carbon is slightly delta positive. So this lone pair of electrons can be given to carbon, and the carbon-oxygen bond breaks, like I mentioned earlier in the previous slides. So first step of initiating a reaction with the aldehyde is going to be a nucleophilic addition reaction. So when it comes to the reaction between aldehyde or a ketone with 2,4-DNP, it's going to be, the first step is going to be a nucleophilic addition reaction. And in the second step, there's going to be a dehydration taking place. So therefore, a water molecule will be eliminated or removed. So we can call this type of reaction a nucleophilic addition elimination reaction. A nucleophilic addition elimination reaction. First step is a nucleophilic addition. Second step is a dehydration where a water molecule will be eliminated. So therefore we call this a nucleophilic addition elimination reaction. So when it comes to this aliphatic aldehyde and ketones, you can see they will give you a positive test or positive answer 2,2,4-DNP by producing a bright orange color or yellow orange color precipitate. When it comes to aromatic aldehydes and aromatic ketones also, the observation is the same. You are going to get a yellow orange color precipitate. So you have benzaldehyde here and we have acetophenone here. When you react both of those with 2,4-DNP, you are going to observe the formation of a yellow orange color precipitate, and how the reaction takes place is given here. So keep in mind, students, always the oxygen that is present here gets removed along with the two hydrogens connected to the nitrogen atom that we find over here. So they will get removed as a water molecule. So apart from this main product, we do have a water molecule also that is being produced. In the previous two steps also, you have to keep in mind, apart from the main product, we do have water being produced here as well. That is something we should not forget. Right. So both aliphatic and aromatic aldehydes and ketones answer to 2,4-DNP or 2,4-dinitrophenyl hydrazine. Reactions with acidified potassium permanganate. An acidified solution of potassium permanganate can be formed by adding dilute sulfuric acid. So we are going to be using dilute sulfuric acid for this. We can use dilute sulfuric acid to acidify the potassium permanganate solution we have, and we can form the oxidizing agent acidified potassium permanganate. This solution can react as an oxidizing agent. This reagent will oxidize aliphatic aldehydes to form the corresponding carboxylic acid. So if you take an aldehyde and react it with an oxidizing agent such as acidified potassium permanganate, you will get a carboxylic acid. However, no reaction is observed with aliphatic ketones. Aliphatic ketones do not react with acidified potassium permanganate. Now students, for the oxidation to take place, there should be at least one hydrogen connected to the carbonyl carbon. When it comes to ketones, we don't have that. We don't have at least one hydrogen connected to the carbonyl carbon. When it comes to ketones, from both sides you have a alkyl group connected to the carbonyl carbon. There are no hydrogens directly attached to the carbonyl carbon when it comes to ketone, when it comes to aliphatic ketones. So therefore, aliphatic ketones do not answer to this particular test, which is done with the use of acidified potassium permanganate. So acidified potassium permanganate is not capable of oxidizing ketones, but it can oxidize aldehydes. Acidified potassium permanganate will oxidize aromatic aldehydes and ketones to produce benzoic acid. So unlike aliphatic ketones, aromatic ketones do get oxidized in the presence of acidified potassium permanganate. So acidified potassium permanganate will oxidize both aromatic aldehydes and ketones, and it will produce benzoic acid. Any aromatic aldehyde or a ketone will get oxidized to produce benzoic acid. So since benzoic acid is not, now all these reactions are done in aqueous medium, and since benzoic acid is not going to be soluble in water, it is going to separate out as a white color precipitate. During the oxidation process, permanganate ions will get reduced to form Mn2 plus. As you know, students, Mn2 plus solutions are going to be, or they are referred to be pale pink in color. However, when you're observing the color of Mn2 plus in lab environment, it's going to appear colorless. It's difficult to observe the pale pink color of Mn2 plus. It's very hard to observe that pale pink color. So therefore, lower concentrations of Mn2 plus ions will produce a colorless solution. A color change of purple to colorless will be observed. So students, what they're trying to say here is that when you are using acidified potassium permanganate, you can use acidified potassium permanganate to separately identify aliphatic aldehydes and ketones. So if you have a sample of an aliphatic aldehyde and aliphatic ketone, only aliphatic aldehydes will react with potassium permanganate or acidified potassium permanganate. Now, how do we know that it actually reacted with acidified potassium permanganate? Acidified potassium permanganate has a very strong purple color. When the reaction takes place, since potassium permanganate gets used up, or permanganate ion is a reactive species, so since permanganate ion gets used up, the purple color that is brought about by the permanganate ion will disappear. So you will observe a color change from purple to colorless as permanganate ions oxidize the aldehyde. However, when you're talking about a ketone, ketones will not get oxidized by acidified potassium permanganate. So therefore, there won't be a color change. Purple remains purple. When it comes to aromatic aldehydes and ketones, you cannot use acidified potassium permanganate to separately identify aromatic aldehydes from aromatic ketones, because both of them will decolorize acidified potassium permanganate. So therefore, you can't separately identify aromatic aldehydes from aromatic ketones. But apart from the decolorization of the permanganate ion, when it comes to aromatic aldehydes and aromatic ketones, they produce benzoic acid, which is insoluble in water. So therefore, it will precipitate out as a white color precipitate. So apart from the decolorization of permanganate ion, you will observe the formation of a white color precipitate. Because of this, we can use acidified potassium permanganate to identify between aliphatic aldehydes and aromatic aldehydes or ketones. So we can separately identify aliphatic aldehydes from aromatic aldehydes and ketones, because only aromatic aldehydes and ketones will decolorize potassium permanganate at the same time producing a white color precipitate. Aliphatic aldehydes will only decolorize potassium permanganate. They will not form a white color precipitate. So you can see over here how the test is done. Take about 5 cubic centimeters of acetaldehyde, acetone, and benzaldehyde dissolved in acetone. This is also very important. Benzaldehyde dissolved in acetone. When you're trying to react acetaldehyde, which is the aldehyde, aliphatic aldehyde we are taking, and acetone, which is the aliphatic ketone we are taking, we didn't dissolve it separately in another solvent. We just took it, dissolved it in acidified potassium permanganate. Why? Because they are water soluble. They will dissolve well in water. And they will react with acidified potassium permanganate and will give us an answer. So you can see when formaldehyde or when acetaldehyde reacts with acetate potassium permanganate, they will form the corresponding carboxylic acid. And this will create a color change, which is from purple to colorless. When it comes to ketones, when you take acetone, we know acetone is a ketone. It doesn't react with acetate potassium permanganate. So when you react acetone with acetate potassium permanganate, the purple color will remain purple. It will not get changed to colorless. So we observe these two observations first, and then we are moving on to aromatic aldehyde, which is benzaldehyde. So when it comes to benzaldehyde, we don't directly introduce it to acidified potassium permanganate. We dissolve the benzaldehyde in acetone. They say we first of all have to dissolve the benzaldehyde in acetone. Why? Because benzaldehyde is water insoluble. Acetone dissolves both in benzaldehyde as well as in water. So therefore, we can use acetone as a co-solvent to aid the dissolving of benzaldehyde in potassium permanganate solution. So students, acetone was used as a co-solvent here. Now you may ask, when it comes to Brady's reagent, we used methanol. Why can't we use methanol here? Why can't we use methanol as a co-solvent? When it comes to Brady's reagent, of course, we did use methanol as a co-solvent. But when it comes to acidified potassium permanganate, we don't use methanol. Instead, we use acetone. What is the reason? Methanol will react with acidified potassium permanganate. Methanol can get oxidized in the presence of acidified potassium permanganate. So it will interfere with our observations, right? So the color of acidified potassium permanganate will anyway be decolorized because methanol will react with it to form a carboxylic acid. When it comes to acetone, we know very well acetone doesn't react with the oxidizing agent acidified potassium permanganate. So therefore, we can use acetone as a co-solvent. It will not interfere with our reaction. So we can use acetone as a co-solvent to dissolve benzaldehyde. So you can see that's a very important point, students. You have to keep that in mind. And then we are going to move on to the remainder of the test. They say add to each test tube acidified potassium permanganate and observe the color change that is taking place. When it comes to aldehydes, we saw potassium permanganate actually decolorizes or gets decolorized in the presence of an aldehyde. If it is aliphatic ketones, we see color of potassium permanganate does not get decolorized. But when it comes to aromatic aldehydes and aromatic ketones, both decolorize acidified potassium permanganate, right? You can see we have here benzaldehyde and it is getting converted into carboxylic acid or benzoic acid here. Corresponding carboxylic acid that we form here is benzoic acid. Benzoic acid is water insoluble, so therefore it will be formed as a white color precipitate. When it comes to acetophenone, when you react it with potassium permanganate, again will get converted into benzoic acid. So potassium permanganate will lose its color. Again, the same product, benzoic acid is insoluble in water, so therefore white color precipitate will be formed. Now students, this is the observation. You have potassium permanganate, which is a purple color solution, and we add our aromatic aldehydes or aromatic ketone, normally dissolved in acetone. So when you take aromatic aldehyde or aromatic ketone and when you react it with acidified potassium permanganate, the color of potassium permanganate will disappear as MnO4 minus, which is permanganate ion, gets converted into Mn2 plus, the color will go from purple to colorless. Apart from that, you can see a white color precipitate gets formed. White color crystalline precipitate will get formed. That is going to be your benzoic acid. Benzoic acid is water insoluble, so it will precipitate out as a white color precipitate. Important. Potassium permanganate can be used to separately identify aliphatic aldehydes and aliphatic ketones. Yes, as I mentioned earlier, if you have two samples of an aliphatic aldehyde and an aliphatic ketone, only the aliphatic aldehyde will decolorize potassium permanganate. But the same potassium permanganate solution cannot be used to separately identify aromatic aldehydes and aromatic ketones. Both aromatic aldehydes and aromatic ketones will decolorize acidified potassium permanganate. So we can't use acidified potassium permanganate to separately identify aromatic aldehydes from aromatic ketones. However, students, we can use acidified potassium permanganate to separately identify an aromatic aldehyde from an aliphatic aldehyde. Why? Because although both of these things will decolorize potassium permanganate, only aromatic aldehydes or only aromatic ketones will produce a white color precipitate while decolorizing the potassium permanganate. Then we move on to another oxidizing agent. Now we looked at acidified potassium permanganate. Now we move on to acidified potassium dichromate. Now, as acidified potassium permanganate reacts with an aldehyde, the color change was from purple to colorless. We have the purple color permanganate ion turning into colorless Mn2 plus ion. When it comes to acidified potassium dichromate, the color change is a bit different to that. So let's dive into this and then we'll discuss the separate color changes. An acidified solution of potassium dichromate can be formed by adding dilute sulfuric acid to a solution of potassium dichromate. This solution can act as an oxidizing agent, yes. This reagent will oxidize aliphatic aldehydes to form its corresponding carboxylic acid. However, no observation is seen with aliphatic ketones. Yes, aliphatic ketones do not get oxidized. We saw it in the previous slides also. When it comes to the oxidizing agent acidified potassium permanganate, aliphatic ketones didn't react. Similarly, potassium dichromate or acidified potassium dichromate will also not be able to oxidize aliphatic ketones. Acidified potassium dichromate will oxidize aromatic aldehydes and ketones to produce benzoic acid. So just like in the previous instance, aromatic aldehydes and aromatic ketones can get oxidized into forming benzoic acid. And benzoic acid is going to be observed as a white color precipitate. During the oxidation process, the dichromate ion, which is orange in color, dichromate ion is orange in color, will get reduced to form chromium 3 plus ions. So chromium 3 plus ions in the medium actually form a complex CrSO4 5H2O plus. So it is not just chromium connected to 6 water ligands. That complex, a hexa aqua chromium 3 complex, usually would be violet in color. But when a chromium ion is present in water alongside other ligands like chloride ions or sulfate ions, they form a complex like this, which happens to be green in color. So most of the time, when chromium 3 plus ions are present in a medium or aqueous medium alongside sulfate ions or chloride ions, the medium will appear green. So that's why we often say chromium 3 plus ion solutions are green in color, because majority of the time sulfate or chloride ions are present in the medium. Because we introduce chromium as chromium chloride or chromium sulfate, so therefore chromium ions are definitely going to be present in the medium. Chloride or sulfate ions will be present in the medium, giving us this green color complex. So now students, if you take a look at this complex, you can see chromium is +3 in charge, sulfate is -2 in charge. So the overall charge of the complex is going to be +1. You can see overall charge of the complex is +1 given on the right hand side. So you can observe this color or green color when dichromate ions get reduced while oxidizing the aldehyde. When dichromate ions get reduced, they form chromium 3 plus ions, and in solution, chromium 3 plus ions will appear green in color due to formation of complexes, like the complex that we have written over here. So the color change would be from orange to green. When they oxidize an aldehyde, the color change would be from orange to green. When it comes to ketones, ketones do not get oxidized. Aliphatic ketones do not get oxidized by acidified potassium dichromate. So do you see this color change? No. If there was an aliphatic ketone, the orange color dichromate ion will remain as the orange color dichromate ion. Why? Because the ketone will not react with the orange color dichromate ion. Aliphatic ketones do not react. So let's take a look at how the test is done again. Take about 0.5 of acetaldehyde, acetone and benzaldehyde dissolved in acetone, like I mentioned earlier. When it comes to taking benzaldehyde, they have taken it dissolved in acetone to make sure that it dissolves well in water. In 3 different test tubes, add to each test tube acidified potassium dichromate and observe any change that takes place. When it comes to we have formaldehyde and acetaldehyde given here, or methanal and ethanal given here. When you react methanal and ethanal with acidified potassium dichromate, you can see methanal gets converted into methanoic acid, or in common terms formic acid, and ethanal gets converted into ethanoic acid, or in common terms acetic acid, while producing chromium 3 plus ions. So chromium 3 plus ion solutions are going to appear green in color, and we have the orange color dichromate turning into the green color chromium 3 plus ion solutions. The observation is given here. When aliphatic aldehydes are reacted with acidified potassium dichromate, it will convert into the corresponding carboxylic acid while producing chromium 3 plus ion solutions, which appear green in color. So what about aliphatic ketones? If you take an aliphatic ketone such as this one, if you react it with acidified potassium dichromate, will there be a reaction? No, there will be no reaction. There will be no reaction. Aliphatic ketones will not react with acidified potassium dichromate. Aromatic aldehydes and ketones. So just like when it comes to acidified potassium permanganate, with aromatic aldehydes and aromatic ketones, they will react with acidified potassium permanganate. Both of them, not just the aldehyde. Both aromatic aldehyde and both aromatic ketone will actually react with acidified potassium permanganate to form benzoic acid. Benzoic acid is water insoluble, so you're going to observe this as a white color precipitate. As you can see here, when aromatic aldehyde or aromatic ketone is introduced into the orange color acidified potassium dichromate, you will form a green color solution. Not just the green color solution, there will be the formation of a white color precipitate. You can see over here the formation of white color precipitate also is indicated there. So white color precipitate happens to be the benzoic acid, which is water insoluble. So it will precipitate out as a white color precipitate. Now students, we looked at the oxidizing agents. Two main strong oxidizing agents, which is acidified potassium permanganate and acidified potassium dichromate. Both of those reacted to give a positive answer with aliphatic aldehydes, but aliphatic ketones did not answer to both of those oxidizing agents. When it comes to aromatic aldehydes and aromatic ketones, both aromatic aldehydes and ketones give positive answers to these oxidizing agents. So therefore, you can't separately identify aromatic aldehydes from aromatic ketones with the use of the oxidizing agents we observed before. Now, we move on to reactions with Tollens reagent. So Tollens reagent is also referred to as ammoniacal silver nitrate. Ammoniacal silver nitrate. So this reagent contains silver plus ions. Now silver plus ions present in this reagent can act as a mild oxidizing agent, oxidizing aldehydes. Ammoniacal silver nitrate is known as Tollens reagent. Tollens reagent is capable of oxidizing aldehydes while getting reduced. So Tollens reagent contains silver plus ions. These silver plus ions can get reduced to silver solid. When Tollens reagent is reduced, it forms solid silver. Solid silver being one of the most important things in this reaction, which will get coated on the interior walls of the test tube where the reaction is normally carried out to produce a silver mirror effect on the test tube. Now students, if this is the test tube, when you have your Tollens reagent in the test tube and when you add an aldehyde, we have to heat it up in a water bath. The aldehyde gets oxidized to form the carboxylic acid. So we know if one species is getting oxidized, there has to be another that is getting reduced. So when the aldehyde is getting oxidized, the silver plus ions in the Tollens reagent get reduced. Silver plus gets converted into silver solid. So the silver solid that is formed actually gets coated on the interior walls of the test tube or the boiling tube that you are carrying the test in. So if this is the test tube, in the interior walls of this test tube, the silver solid will get coated. So as the silver solid gets coated, it creates a nice mirror effect on the test tube. You can actually see yourself in that particular mirror that it creates. So it's a very interesting experiment that you can do in the lab. Most students love it because it's a very rare experiment, or you wouldn't necessarily come across it on a daily basis, I would say. So therefore, it's a very interesting observation, and we call this test the silver mirror test. Silver mirror test can be used to identify the presence of an aldehyde. Only aldehydes answer to this test. there's one carboxylic acid answering to this test, that is formic acid or methanol. That is also because methanol contains an aldehyde group in it. So therefore, aldehydes answer to the silver mirror test, producing the positive observation, which is the formation of a silver mirror. Right. Ketones do not react with tolerance reagent. Very, very important. Ketones do not react with this tolerance reagent. Due to this reason, the use of tolerant reagent to identify aldehydes from ketones is also known as the silver mirror test. Due to the formation of a silver mirror, we can actually call this test the silver mirror test, and we can use it to identify aldehydes from ketones. Preparation of tolerance reagent. You actually have to prepare the tolerance reagent at the labs. So we can actually prepare the tolerance reagent with the use of silver nitrate. Take about 1 cubic centimeter of silver nitrate solution in a clean test tube and add a drop of sodium hydroxide. So as you add a drop of sodium hydroxide, you form silver hydroxide. So you take silver nitrate, AgNO3, and to it you add a drop of sodium hydroxide. And what you form is silver hydroxide along with sodium nitrate. Silver hydroxide along with sodium nitrate. But students, sodium hydroxide is not stable. So therefore, it dissociates. Silver hydroxide, since it is not stable, will dissociate into forming Ag2O, silver oxide, releasing water. So we have to balance this equation now. Now it is balanced. You can see 2 silver on the left hand side, 2 silver on the right hand side, 2 oxygens, 1 oxygen here, 1 oxygen here, so 2 oxygens on the right hand side also, 2 hydrogens on the left hand side and 2 hydrogens on the right hand side, completely balanced. So as you can see, 2 silver hydroxides turn into silver oxide. So that is why you can see the reaction over here. We have directly written down here, 2 silver nitrate react with 2 sodium hydroxide to produce 1 silver oxide, sodium nitrate and water. Sodium nitrate and water. Basically, to obtain 2 silver hydroxide over here, you have to multiply everything by 2. And that's how we got to the equation that is written here. 2 silver nitrate, sodium hydroxide going to silver oxide, sodium nitrate and water. So silver oxide, then later on they say after obtaining silver oxide, you are going to add ammonium hydroxide after obtaining silver oxide brown color. Silver oxide is a brown color precipitate. So after obtaining this brown color precipitate, we are going to start adding ammonium hydroxide or aqueous ammonia. And we are going to add it drop-wise only until the point where all the brown color precipitate completely dissolve. So you will add ammonium hydroxide drop-wise until all of the silver oxide precipitate is just dissolved. And at that point, you would have formed your ammoniacal silver nitrate clear solution. So the formation of ammoniacal silver nitrate is given here after the forming of silver oxide. When you're adding aqueous ammonia or ammonium hydroxide drop-wise, what you're going to get is a complex between silver and ammonia ligands. So the name of this particular complex that is formed is diamine silver 1. Since it is attached to hydroxide ions, is going to be diamine silver 1 hydroxide, and it's going to be a colorless solution. So students, very easy way of producing tolerance reagent or ammoniacal silver nitrate. You take silver nitrate, you add a drop of sodium hydroxide to produce silver oxide, which is a brown color precipitate, and you're going to start adding aqueous ammonia until all of the precipitate is completely dissolved. So when all of the precipitate is completely dissolved, you have a complex formed between silver and ammonia, which is diamine silver 1 hydroxide, diamine silver 1 hydroxide, which is our tolerance reagent. So we can use this now to identify aldehydes. Let's move on to the next slide. Reactions with tolerance reagent. Tolerance reagent is a weak oxidizing agent. It's a weak oxidizing agent. It is a colorless alkaline solution. Yes, we use ammonia to dissolve the precipitate. So therefore, the medium is alkaline. Aldehydes will get oxidized to the corresponding carboxylic acid in the presence of tolerance reagent. So aldehydes can get oxidized because when it comes to tolerance reagent is sufficiently strong enough to convert aldehydes into carboxylic acids. Due to the medium being alkaline, the carboxylic acid that is formed will react with the medium to produce a carboxylate salt. So we will not have the final product as a carboxylic acid because the medium is alkaline. So therefore, the carboxylic acid will react with the medium and form a salt. When the reaction is taking place, the silver plus ions will reduce to form silver solid, which results in the forming of the silver mirror. So silver plus ions will turn into silver solid, which forms the silver mirror. Now students, you can see the reaction that is taking place. You can see a general aldehyde that is given over here, an alkyl group connected to the carbon compound. So you can see this is an aldehyde group that we have over here, and you have our tolerance reagent. And when they react, you can see the formation of a carboxylate anion. You can see the aldehyde group getting converted into or oxidized into forming a carboxylic acid, and you can see the carboxylic acid has reacted with the ammonia in the medium to form ammonium carboxylate salt. Apart from that, one ammonia ligand, or actually the ammonia ligands that were present over here, 3 of them have been released over here along with some water. Now, the observation here is that the silver plus ions in the tolerance reagent, they get reduced to form silver solid, which actually is the reason for that silver mirror observation. So oxidation number goes from +1 all the way to 0. +1 all the way to 0. When it comes to an aldehyde that looks like this, the oxidation number of carbon will be +1, and when it converts into carboxylate anion, we are going to have an oxidation number over here which is +3. You're going to have +3 oxidation number here on the carbon. So +1 to +3 is the oxidation number change. So there's the involvement of 2 electrons here. There's involvement of 2 electrons here when it comes to oxidation. When it comes to reduction of one silver ion, there's involvement of 1 electron. However, there are 2 silver ions getting reduced to form silver solid. So therefore, there's an involvement of 2 electrons there. So 2 electrons are taken in when it comes to the reduction, and 2 electrons are released when it comes to the oxidation process. So that is just to give an idea about what takes place when it comes to oxidation and reduction. Now we move on to the observation. You can see the observation that is taking place, or what you can actually observe when you're conducting this experiment, which is a very nice observation. You're going to take tolerance reagent into a test tube, and we are going to add the aldehyde, and we are going to place the test tube in a water bath. And if you allow it to continue the reaction for a while, you're going to observe the formation of a silver mirror. You're going to observe as the reaction proceeds, silver solids starts to deposit in the interior walls of the test tube, forming this beautiful observation, which is a silver mirror. So silver mirror test can actually be used to identify aldehydes from ketones. So as a summary, ammoniacal silver nitrate or tolerance reagent can be used to identify aldehydes from ketones. Aldehydes will form a silver mirror when reacted with tolerance reagent. So therefore we call this a silver mirror test. Ketones do not answer to the tolerance reagent. There is no observation when you are reacting ketones with the tolerance reagent. With that, we move on to the next test, which is the reaction with Fehling's solution. Fehling's also is an oxidizing agent which is capable of oxidizing aldehydes. Fehling's solution can be used to identify aldehydes from ketones, very much like ammoniacal silver nitrate or tolerance reagent. We can use Fehling's also to identify aldehydes from ketones. But keep in mind, we are not going to be observing a silver mirror when it comes to Fehling's solution. The observation is the formation of a brick red color precipitate. So Fehling's will identify the presence of an aldehyde by forming a brick red color precipitate. When it comes to tolerance, you will see the formation of a silver mirror. When aliphatic aldehydes are heated after mixing with Fehling's solution, a brick red color precipitate will be formed. So the observation is a formation of brick red color precipitate, only formed when Fehling's is reacted with aldehydes. Ketones do not answer to Fehling's test. Ketones will not show this observation as they do not react with Fehling's solution. Aromatic aldehydes do not show a positive result for Fehling's test. Aromatic aldehydes do not show a positive result. Aromatic aldehydes will not show a positive result for this test. This is because the reaction between Fehling's solution and aromatic aldehydes are extremely slow to the point where there will not be an observable color change within a reasonable time frame. So students, this reaction between aromatic aldehydes and the Fehling's solution happens extremely slowly to the point where you will not be seeing a formation of a precipitate when you're conducting this in the lab. So therefore, you will not be able to use Fehling's solution to identify between aromatic aldehydes and aromatic ketones, because even aromatic aldehydes do not answer to Fehling's test. However, aliphatic aldehydes and aliphatic ketones can be separately identified with the use of Fehling's solution. Fehling solution will produce a red or brick red color precipitate when reacted with aliphatic aldehydes. Aromatic aldehydes, on the other hand, will not give this observation. Fehling's solution have to be prepared in the lab. So you can prepare the Fehling's solution in the lab by following these instructions. Fehling's solution can be made by mixing equal volumes of Fehling's A and Fehling's B together. Fehling's A solution is made by dissolving copper sulfate 5H2O or hydrated copper sulfate, which is commonly available in the lab. So now will be a good time to remember the blue color copper sulfate crystals that you find in the lab is hydrated copper sulfate. The anhydrous copper sulfate will appear white in color. So the white color copper sulfate solid that you might have come across in the lab is your anhydrous copper sulfate. If it gets exposed to moisture, it will also turn into a blue color solid. So copper sulfate 5H2O solid crystals are dissolved in water acidified with a few drops of concentrated sulfuric acid. So we form phalanx A. We form phalanx A by dissolving copper sulfate hydrated solid in water that is acidified with concentrated sulfuric acid. Then we move on to phalanx B solution. Phalanx B solution is made by dissolving a mixture of solid potassium sodium tartrate. We'll take potassium sodium tartrate. The formula of potassium sodium tartrate is given here. And solid sodium hydroxide in water. So you take a mixture of, or you take a little bit of solid sodium or potassium sodium tartrate, and you take small amount of sodium hydroxide pellets that you have abundantly in the lab, and you mix these two together in a beaker, two solids, you have it in a beaker, and then you will add a little bit of water and dissolve the two together. Now you have your phalanx B solution. So phalanx B solution contains what? Potassium sodium tartrate, sodium hydroxide dissolved in water. And then these two solutions are mixed. Most of the time equal volumes of each solution will be taken, and you will mix them together, and you'll be forming a dark blue color solution. You'll be forming a dark blue color solution, which happens to be your phalanx solution. So dark blue color solution that is formed is going to be your phalanx solution. So this is how, students, we obtain our phalanx solution. Let's take a look at the reaction that is taking place. You can see copper sulfate and sodium hydroxide and sodium potassium tartrate are now in the mixture, because we took, when it comes to phalanx A, copper sulfate dissolved in sulfuric acid, and when it comes to phalanx B, we had sodium hydroxide and potassium sodium tartrate. So you can see all of them are present here. And when these two react, you can see the formation of the complex that is referred to as our phalanx solution. So dark blue color of the phalanx solution is due to the formation of this complex. So we have copper 2+ ions are forming dative covalent bonds with this particular compound, which happens to be our phalanx solution. Apart from that, in the phalanx solution there will be sodium sulfate and water, but the main component that we are interested in when it comes to talking about phalanx solution is this complex that we have formed here, the dark blue color complex. This contains copper 2+ ions. Now, with that observation, let's move on to what actually takes place when we are carrying out this experiment. When phalanx solution is heated with an aliphatic aldehyde, a brick red precipitate will be formed. So the observation would be the formation of a brick red precipitate. So we have given a generic aliphatic aldehyde. When you add the phalanx solution to it and when you heat it, the copper 2+ ions present in the medium will turn into copper 1+ ions, or copper 1 oxide. Copper 1 oxide happens to be a brick red color precipitate. So students, the dark blue color solution turns into a brick red color precipitate. Actually, when this brick red color precipitate is being formed, the entire solution appears to be turning red or brick red in color. For a while there, you would assume that a red color solution is formed, but upon closer observation, you can see this red color observation that you note is in fact due to the formation of a brick red color precipitate, which is really fine in nature, and this precipitate is dispersed throughout the media, making it look like a red color solution. But it is not a solution, students. In fact, this is a precipitate that is dispersed or suspended throughout the medium, creating the illusion of forming a solution. However, if you allow the precipitate to settle to the bottom for a while, if you allow the precipitate to settle to the bottom for about 5 minutes, you will see that precipitate will separate out to the bottom, and you can very clearly observe the brick red color precipitate after about 5 minutes. Now, the reaction that is taking place when it comes to this test that we do is given here. If you take any aldehyde and react with the copper 2 plus present in Fehling's solution, the copper 2 plus gets reduced to copper 1 plus, and the aldehyde group gets oxidized to form the carboxylate anion. Again, you can see it gets oxidized to carboxylic acid. However, Fehling's solution, or Fehling's B more precisely, was made with the use of sodium hydroxide pellets, indicating resultant Fehling's solution is going to be alkaline. So we have a lot of sodium hydroxide in the medium, so therefore the overall medium is going to be alkaline. So due to that fact, you can see we are forming the carboxylate anion instead of the carboxylic acid. So carboxylate anion will be formed along with copper 1 oxide, which is the brick red color precipitate, and some water will be formed. So this is the reaction, generic reaction for the oxidation of aliphatic aldehyde with the use of Fehling's reagent. So you can use this generic reaction to write an equation for any aldehyde. For example, if someone is asked how acetaldehyde CH3 C double bond OH reacts with Fehling's solution, the ionic equation would be this. Right, so this will be your observation, or this is how you're going to be writing the equation when acetaldehyde or ethanol reacts with Fehling's solution. So when it comes to any aldehyde, you will be able to write its equation like this. With that, we'll move on to the next slide. Ketones plus Fehling's solutions will give us no reaction. So when it comes to ketones, if you take any aromatic aldehyde, or actually not only ketones, aromatic aldehydes or aromatic ketones will also not answer to the Fehling's solution. So you have to keep that in mind. Unlike Tollens reagent actually does answer, or when it comes to aldehydes and ketones, aromatic aldehydes do answer to the Tollens reagent test. But when it comes to Fehling's reagent, you will not see aromatic aldehydes, giving us a positive answer to the Fehling's test. When you are reacting aromatic aldehydes or aromatic ketones with Fehling solution, you will not see the formation of brick red precipitate. Instead, you will see a blue color solution remaining without undergoing any change. When it comes to ketones, aliphatic ketones or aromatic ketones, both of them will not react with Fehlings to produce a brick red precipitate. So there's no reaction with ketones also. So the only thing that answers to Fehling's test is aliphatic aldehydes. Aliphatic aldehydes will react with Fehling solution to produce a brick red color precipitate. With that, students, we come to a summary, and this is summary of all the tests that we conducted in this experiment. So let's take a look at each of the reagents that we have used and the observations that we have over here. Tests and observations of aldehydes and ketones. Compounds are given here. We can see we have used methanol, ethanol, propanone or 2-propanone. We have benzaldehyde and acetophenone given here on the first column. And the reagents we have used are acidified potassium permanganate, acidified dichromate, Brady's reagent, and we have Tollens reagent and Fehling's solution. So when it comes to reacting potassium permanganate with aliphatic aldehydes, what is observation? Now I will make another important distinction here. All of these are aliphatic compounds, and one of them is an aliphatic ketone. So we'll write that first. We'll write that this is a ketone and these two are aldehydes. And all of these are aliphatic. All these are aliphatic aldehydes and ketones. When it comes to these two, you can see the very first aromatic compound that we have here is an aldehyde, and then we have a ketone, and both of these compounds are aromatic compounds. So that's a distinction that would help you when you're talking about the observations. Right, so we have methanol and ethanol, both are aliphatic aldehydes. So they react with acidified potassium permanganate. The purple color will be decolorized. As you know, aliphatic aldehydes get oxidized in the presence of acidified potassium permanganate. But what about ketones? They do not react with acidified potassium permanganate. Ketones, aliphatic ketones, do not get or do not react with acidified potassium permanganate. What about aromatic aldehydes and aromatic ketones? They do react with the oxidizing agent acidified potassium permanganate, and the purple color of the acidified potassium permanganate will be decolorized while producing a white color precipitate. White color precipitate is produced due to the formation of benzoic acid. So this CHO group gets converted into a COOH group, forming benzoic acid. which is insoluble in water. So therefore, we have this white color precipitate formed. So purple color decolorized, white color precipitate formed when it comes to acetophenone. Also, you are going to observe the purple color decolorized and the white color precipitate formed. Purple color also will get decolorized. When it comes to acetophenone, also you can see it reacts with acidified potassium permanganate. Then we move on to acidified potassium dichromate. Acidified potassium dichromate will oxidize aliphatic aldehydes. So both of the ethanal and methanal actually will react with acidified potassium dichromate. And the orange color of the potassium dichromate will get converted into a green color due to the dichromate ion turning into chromium 3+ ion. So the orange color turns green. When it comes to methanal, ethanal also will give the same observation. However, aliphatic ketones will not give this color change. They will not react. So aliphatic ketones, do they get oxidized with acidified potassium permanganate or acidified potassium dichromate? No. With both of those oxidizing agents, aliphatic ketones do not react. But when it comes to aromatic aldehydes and aromatic ketones, both of them, we have benzaldehyde and acetophenone, both of them will react with acidified potassium dichromate and will turn the orange color of dichromate into a green color while producing benzoic acid, which is the reason for the formation of a white color precipitate. You can see even acetophenone, which is a ketone, aromatic ketone, will turn orange color dichromate ion to a green color while producing a white color precipitate. What about Brady's reagent? Now, students, Brady's reagent is mainly there to identify any carbonyl compound. So, regardless of whether the carbonyl compound is aromatic or aliphatic, Brady's reagent can be used to identify the presence of the carbonyl group. So, therefore, Brady's reagent is most of the time used to identify carbonyl compound from other organic compounds like alcohols. So, in the presence of Brady's reagent, all carbonyl compounds, regardless of whether they are aldehydes or ketones or aliphatic or aromatic, will give a positive answer of forming a yellow-orange color precipitate or a bright orange color precipitate. We can see all have answered to Brady's. Now, when it comes to Tollens reagent is usually used to identify aldehydes. Tollens reagent will form a silver mirror when aliphatic or aromatic aldehydes are reacted with Tollens reagent. We can see we have two aliphatic aldehydes. We have methanal and ethanal. Both methanal and ethanal will answer to Tollens reagent by forming a silver mirror. And then we have an aromatic aldehyde, benzaldehyde. Benzaldehyde also formed a silver mirror. So therefore, aliphatic aldehydes and aromatic aldehydes both will answer to the Tollens reagent, forming a silver mirror. But when it comes to ketones, aliphatic ketones or aromatic ketones, they do not answer to the Tollens reagent test or silver mirror test. There is not going to be a silver mirror formed when reacting aliphatic ketones or aromatic ketones with Tollens reagent. What about Fehling's solution, this dark blue color solution? Fehling's solution will answer to aliphatic aldehydes. When it comes to all other compounds like aliphatic ketones, aromatic aldehydes and aromatic ketones will not answer to failings. Only aliphatic aldehydes will answer to failing solution. You can see when you are talking about methanol and ethanol, the formation of a brick red color precipitate is observed, but all the rest, when it comes to aliphatic ketones, we have used acetone here. It is not answering to failing solution. Benzaldehyde or acetophenone, they will also not answer to failings solution. So this is a summary of the theory parts that we have learned about aldehydes and ketones. With the use of the theory knowledge, we can now move on to the lab to actually conduct this experiment and observe these interesting color changes and other observations. Let's move on to the lab now. GCE Advanced Level Chemistry Practical Series, Experiment number 27, Tests for Aldehydes and Ketones. And in this practical, we will be focusing on observing the characteristic reactions involving aldehydes and ketones. Let's move on to identifying the reagents we will be using for this practical. These are the reagents we will be using for this practical. We will be using methanol, also known as formaldehyde, ethanol, known as acetaldehyde, 2-propanone, also known as acetone, and we will be using benzaldehyde, acetophenone, and methanol. To test these things, we will be using reagents such as 2,4-DNP, which is known as 2,4-dinitrophenyl hydrazine, 2,4-dinitrophenyl hydrazine. It is commonly known as Brady's reagent as well. We have potassium permanganate, KMnO4, potassium dichromate, K2Cr2O7, which is orange in color. Potassium permanganate is purple in color. I'm pretty sure by now you are familiar with these colors. We have tolerance reagent. What we have here as tolerance reagent is ammoniacal silver nitrate. So make note of that as well. We have our failing solution, a solution made with two components, which is failings A and failings B. More information about that will be delivered to you when we are doing the experiment using failings reagent. Apart from that, we'll be using some test tubes, a wash bottle, and a few droppers as well. Let's move on to our first experiment, solubility of these aldehydes and ketones in water. To see the solubility of water of these aldehydes and ketones that you have over here, we will be taking each of these aldehydes and ketones, or we can call them carbonyl compounds, and we will dissolve small amounts of them in a little bit of water. If you do not see a layer separation, that means it is soluble in water. Once you observe two layers being formed, that indicates that that particular aldehyde or ketone is not soluble in water. Let's take a small test tube and let's take formaldehyde or methanol and transfer small amount of methanol into a test tube. So now we have taken small amount of methanol into a test tube like this. You can see the colorless layer over here is our organic layer, which is the methanol layer. Now to this, we will add a little bit of water to see if this methanol is soluble in water. We have our wash bottle containing distilled water. So let's add small amount of water to see if it is soluble in water. As you can see, upon addition of water, we do not see two layers forming here, which means that methanol was completely miscible in water, or it is soluble in water. So you only see a single layer. You do not see formation of two layers, indicating that methanol is soluble in water. Now let's move on to ethanol or acetaldehyde. So you have here your ethanol reagent. We will take small amount of ethanol into a test tube. We can see a clear layer over here that is containing ethanol. And like in the previous experiment, we will add a little bit of water to see if ethanol is soluble in water. You can see after addition of water and after I shake it a little bit, after I shake the test tube a little bit, you do not see formation of two layers, indicating ethanol is soluble in water. Does this mean all the aldehydes are soluble in water? Not necessarily. Not all the aldehydes are soluble in water. Aldehydes with shorter carbon chains are soluble in water, whereas aldehydes containing lengthier carbon chains or long carbon chains are insoluble in water. The reason for this is when a carbon chain is extremely long or considerably long, that entire aldehyde molecule will become nonpolar. So this nonpolar nature of those aldehydes will not allow those aldehyde molecules to dissolve in a polar solvent like water very well. So that is why we see short chains aldehydes like methanol and ethanol dissolving well in water. Let's move on to a ketone. So we have here 2-propanone. Now 2-propanone is commonly referred to as acetone. I'm pretty sure that most of you are very familiar with acetone. So we will take our 2-propanone and let's see if it is soluble in water. We'll take a test tube and transfer a small amount of propanone or 2-propanone into a test tube and add small amount of water with the help of our wash bottle. Here you can see on addition of water into 2-propanone, we did not form two separate layers, indicating that 2-propanone or acetone is soluble in water or miscible in water. So does that mean all the ketones are soluble in water? Again, not necessarily. Short chain ketones are soluble in water just like in aldehydes, and when the carbon chain is longer, the ketones will become insoluble in water. Keeping that in mind, let's move on to an aromatic aldehyde, benzaldehyde. We have here an aromatic aldehyde, which is benzaldehyde. Let's see if that is soluble in water. We'll take a test tube and we will add benzaldehyde into this test tube. We'll take a small quantity like this of benzaldehyde. Now to this, let's add a little bit of water. You can see when water is added, we can very clearly see formation of two layers. At the bottom of this test tube, we have our benzaldehyde. It's high in density, so it has sunk to the bottom, and over on the top of this particular test tube we can see a layer of water present. So this indicates, now if I give it a little shake, you can see we can try to dissolve it, but if you leave it for a while, we can see the tiny droplets that are formed due to shaking of this test tube again sink to the bottom. Tiny droplets of benzaldehyde that is formed actually sink to the bottom and separate into two layers as before. So this indicates that the benzaldehyde that we have here is insoluble in water. It is mainly nonpolar in nature, so it does not necessarily dissolve well in water. So you can see the formation of two layers. Let's take a look at acetophenone, which is an aromatic ketone. So we will take a little bit of this aromatic ketone into a test tube. You can see acetophenone present here. Then we'll add a little bit of water to this. You can see when we add water, acetophenone remains at the bottom as a separate layer and water is present on top as a separate layer. So water and acetophenone are now present as two separate layers, indicating that acetophenone does not dissolve in water. Even if you shake it, you can see acetophenone droplets are formed, but after shaking for a while, acetophenone will sink to the bottom due to its high density and separate out as two layers. Right? So this indicates very clearly acetophenone is not soluble in water. So to summarize, we saw that when we are dissolving aldehydes and ketones, aldehydes or ketones that contain short carbon chains actually dissolve well in water. However, if we are moving on to aromatic aldehydes or aromatic ketones, or aldehydes or ketones with lengthier carbon chains, we saw that those are not soluble in water. So we have here formaldehyde was soluble in water. You do not see a layer separation there. Then we had acetaldehyde or ethanol, which is soluble in water. You do not see a layer separation there. We have acetone or 2-propanone, soluble in water, did not form two separate layers. We have benzaldehyde, which was not soluble in water, so two separate layers were formed. Finally, we have our acetophenone, again was not soluble in water, so therefore two separate layers were formed. Now let's move on to reacting these aldehydes and ketones with 2,4-DNP. We are going to test how the aldehydes and ketones react with 2,4-DNP, 2,4-dinitrophenyl hydrazine, or commonly known as Brady's reagent. So over here we have two aliphatic compounds and two aromatic compounds. What we have here is an aliphatic aldehyde, an aliphatic ketone, and then we have an aromatic aldehyde and aromatic ketone. So we are going to see how aliphatic carbonyl compounds and aromatic carbonic compounds react with 2,4-DNP. So let's take a test tube and take our 2,4-DNP reagent so that you will be able to observe the color of 2,4-DNP. We'll take a small amount of 2,4-DNP. to our test tube here. So we have our 2,4-DNP solution over here. We can see a characteristic orange yellow color. So to a different test tube, we will take our aliphatic aldehyde, which is acetaldehyde, or in other words known as ethanol. We'll take a small amount of ethanol into this test tube. To this, we'll add a little bit of water to make an aqueous solution of ethanol. And to this, we will add our 2,4-DNP solution. Please note the observations when I mix these two. As you can see, as soon as 2,4-DNP is added to this aqueous ethanol solution, we started forming a yellow-orange precipitate. So this yellow-orange precipitate is the positive answer to 2,4-DNP test. You can see the 2,4-DNP has a different color to this, and as soon as 2,4-DNP is added onto our ethanol solution here, you can see the formation of a yellow color precipitate. Let's give it a little mix. Now you can see the 2,4-DNP, upon addition of 2,4-DNP, a precipitate is formed which is yellow-orange in color. This is a positive answer to our 2,4-DNP test, indicating we have a carbonyl compound here. Let's move on to 2-propanone. Let's take a new test tube, and we'll take our 2-propanone here. And to this test tube, we will add small amount of acetone or 2-propanone, and we'll add a little bit of water into this. Now we have our mixture with acetone and water. To this, we will add our 2,4-DNP solution. You can see, upon addition of 2,4-DNP, a yellow-orange color precipitate formed. Different types of aldehydes and ketones form slightly differently shaded precipitates here. So you can see these two precipitates are not the same color. We will add a little bit of 2,4-DNP to increase the color that you see here. But you can see the two precipitates that you form are not the same color. They vary in color from yellow-orange to sometimes even yellow-red color. So we saw that acetaldehyde and acetone both answered positively to the test with 2,4-DNP. So those are all aliphatic compounds. Let's move on to our aromatic compounds. Before that, we need a little bit more 2,4-DNP. So we'll take some more 2,4-DNP into a test tube. We have taken another additional amount of 2,4-DNP into a separate test tube to to react with our aromatic carbonyl compounds. And we will now take one of our aromatic aldehydes that we have here, which is benzaldehyde. We'll take a small amount of benzaldehyde into a new test tube. Now I have taken a small amount of benzaldehyde into our test tube. So as you saw earlier, benzaldehyde does not mix well with water. So what we can do to carry out this experiment is to introduce a co-solvent, a solvent that dissolves both in benzaldehyde as well as in water. So we will be taking methanol as our co-solvent. That is what our textbook suggests. So we will take methanol as our co-solvent, and we will add small amount of methanol into this test tube. Now as you can see, when I added methanol into this test tube, it mixed well with the benzaldehyde that was there in this test tube. So methanol and benzaldehyde mix well with each other. Now I'll be adding Brady's reagent into this mixture. So we have our Brady's reagent here. Let's add small amount of Brady's reagent into our mixture here. As you can see, as soon as we add Brady's reagent, the color starts to change. So this color change indicates the presence of a carbonyl compound. So when I add a little bit of water, you can see the color change a bit more clearly. So you can see a precipitate that has formed. At the bottom, you can see the formed precipitate. A yellow-orange precipitate is formed. This is indicative of the fact that benzaldehyde is indeed a carbonyl compound that reacts with Brady's reagent. Let's take a look at an aromatic ketone. We have here acetophenone, which is an aromatic ketone. So we'll take a small amount of acetophenone into a test tube. And to this acetophenone, we will add a little bit of methanol, right? Like in the previous experiment with benzaldehyde, we have to add methanol to make sure that this acetophenol dissolves well with the 2,4-DNP. So we will add a small amount of methanol. And now, to this methanol acetophenone mixture, let's add our 2,4-DNP. You can see upon addition of 2,4-DNP, the color of the solution changed. We'll have to add a little bit of water to see this clearly. So we'll add a little bit of water here. Now we can see the formation of the yellow-orange color precipitate very clearly. At the bottom you can see that it's starting to accumulate there as well. So acetophenone in the presence of 2,4-DNP, will be forming a yellow-orange precipitate as well. So let's move on to our summary. So as you know, 2,4-DNP, 2,4-dinitrophenylhydrazine, is used to identify carbonyl compounds. Regardless of whether the carbonyl compound is aliphatic or aromatic, it will answer to the 2,4-DNP test. The positive answer to the 2,4-DNP test will be the formation of a yellow-orange precipitate. As you can see, when we reacted acetaldehyde, a yellow-orange precipitate was formed. You can see by the cloudy nature of this solution over here that this is due to formation of tiny, fine particles of precipitate that turns the entire aqueous medium into a yellow-orange suspension. And then we reacted acetone with 2,4-DNP. You can see again a cloudy precipitate is formed here due to the reaction of acetone with 2,4-DNP. Now, when you are forming different types of precipitates here with 2,4-DNP, you can see the colors that are present are different. They will not all be the same color. Depending on the aldehyde or the ketone that you're using, the color of the precipitate may slightly vary. And then we took an aromatic aldehyde, benzaldehyde. You can see upon addition of 2,4-DNP, benzaldehyde started forming a yellow-orange color precipitate. Now this precipitate is more towards the orange color. And then upon addition of 2,4-DNP to acetophenone, it also formed an orange or yellow-orange color precipitate, as you can see here. So finally, you have to make the observation that upon addition of 2,4-DNP, all the aldehydes and ketones will answer positively as long as we are reacting 2,4-DNP with the carbonyl compounds, all the carbonyl compounds, regardless of whether they are aliphatic or aromatic, will answer positively to the 2,4-DNP test. Let's move on to the reactions of aldehydes and ketones that you see with potassium dichromate. In this section of the practical, we are going to see how aldehydes and ketones react with acidified potassium permanganate. Here we have our acidified potassium permanganate solution. Like in our previous experiment, we have two aliphatic compounds and two aromatic compounds. For our aliphatic aldehyde, we have acetaldehyde and we have acetone as our aliphatic ketone. For our aromatic aldehyde, we have benzaldehyde over here, and for our aromatic ketone, we have acetophenone. So now we'll move on to our aliphatic aldehyde and ketone. First of all, we'll take a small amount of our aliphatic aldehyde into a test tube labeled A. Into this test tube, let's add a small amount of our aldehyde, which is acetaldehyde or ethanol. We only need to take a small amount. And to this, we will add acidified potassium permanganate. This potassium permanganate is acidified. As you can see, upon addition of acidified potassium permanganate, very quickly the solution is turning colorless. So in the presence of ethanol or acetaldehyde, you can see acidified potassium permanganate got decolorized. What happened there? What happens here is, since acidified potassium permanganate is a good oxidizing agent, the acetaldehyde that we used, or ethanol that we used, got oxidized to ethanoic acid. So the ethanol that we used got oxidized to ethanoic acid. Now let's move on to our aliphatic ketone. For our aliphatic ketone, we have 2-propanone, or commonly known as acetone. So let's take our test tube that is labeled B. So to this test tube that is labeled B, I will be adding a little bit of our acetone reagent we have here. As you can see, I have taken small amount of acetone here. To this, I will be adding acidified potassium permanganate. So we have our acidified potassium permanganate here. And now I'll be adding acidified potassium permanganate into our acetone that we have here in our test tube. So unlike in the previous example, when I added acidified potassium permanganate into acetaldehyde we have here, we saw potassium permanganate got decolorized. But here we still see the color of potassium permanganate. This could be due to 2 reasons. It could be that acetone does not react with potassium permanganate, or the reaction is slow at room temperature. You do not see a drastic color change. So to avoid having a doubt about that, we will heat this reaction mixture up to see if this reaction takes place at a higher temperature. So if it does not decolorize at that point, we can be sure that in the presence of acidified potassium permanganate, there will be no reaction with acetone. So to avoid having any doubts, we will now give this mixture some heat through a water bath. I will place this test tube labeled B on a water bath, and to make sure that we have a controlled reaction, I will take a small amount of acidified potassium permanganate into another test tube, and now this test tube is not labeled. I'm going to place this control test tube on the water bath as well to see if there's any color change that is happening when you heat potassium permanganate. So let's include this test tube as well in our water bath. Students, it has been a while now. I have allowed it to heat up for a while. Now let's see what has happened after we provided it some heat. So we have here our 2 mixtures. So we have the test tube labeled B, which had potassium permanganate, acidified potassium permanganate and acetone. And on the other beaker on my left hand, we have our potassium permanganate solution that is acidified. So upon heating these two, we saw that no reaction took place, that the color of acidified potassium permanganate did not change, as well as when we try to react acidified potassium permanganate with acetone, we saw that there is no color change. The reason for this is you cannot oxidize aliphatic ketones with the use of acidified potassium permanganate. Although acidified potassium permanganate is a good oxidizing agent, you cannot oxidize aliphatic ketones with the use of acidified potassium permanganate. Now, let's move on to our aromatic carbonyl compounds. We have two aromatic carbonyl compounds here. We'll first take a look at our aromatic aldehyde, which is benzaldehyde. So we have our benzaldehyde reagent here. We will take small amount of benzaldehyde and transfer small amount of it to our test tube that is labeled A. I'm going to be transferring a small amount of benzaldehyde to a test tube labeled A. And to another test tube labeled B, I will be transferring our aromatic ketone. So we have acetophenone as our aromatic ketone. So I'm going to take a small amount of acetophenone and transfer it to this test tube labeled B. Aromatic aldehyde and ketones are not soluble in water, so therefore we are going to be using a co-solvent, which is acetone, before adding potassium permanganate. So let's take acetone or 2-propanone, which we know will not answer to potassium permanganate. So we will be using acetone as a co-solvent because we know that it is not anyway answering to the test that we do with acidified potassium permanganate. So we can use acetone as a co-solvent. Now in our test tube A, we have benzaldehyde. In our test tube B, we have acetophenone. So to each of these test tubes, let's add acidified potassium permanganate. So we have here acidified potassium permanganate. Now we will add small amounts of acidified potassium permanganate into each of these test tubes. You may observe upon addition of acidified potassium permanganate, there is a slight decoloration of the acidified potassium permanganate layer, as well as that they are organized in two layers, right, in both tube A and tube B. That means when you add acidified potassium permanganate to benzaldehyde, you can see over here, the acidified potassium permanganate is starting to lose its color, but this is a very slow reaction. And even when you add acidified potassium permanganate to acetophenone, which is in our tube B, you will see the color has started to decolorize. So now, to expedite this reaction, to make it happen a little faster, let's place both of these test tubes on a water bath. So let's place them on a water bath like so. But before we do, let me give it a little mix. And then let's place, now you can see upon mixing them well, the color of the acidified potassium permanganate almost disappeared, but there's still a persistent color here. But let's place them in a water bath to see if we can get them to be completely colorless. Students, we have allowed the two test tubes to heat up in a water bath for a while now. Let's take them out to see the observations. So in both of these test tubes, we no longer see the color of acidified potassium permanganate. So we do not see the purple color that we saw earlier after we heated them for a while. We still can see a layer separation in both of the test tubes. However, we do not see the purple color. This is because acidified potassium permanganate has oxidized the aromatic aldehyde and the ketone into carboxylic acid, and in doing so, potassium permanganate or permanganate ions have reduced to become Mn2+. And Mn2+ has a very light pink color, but due to the concentration of Mn2+ that we have here, the solutions appear to be colorless. Keep in mind, your observations will be the purple color of acidified potassium permanganate becomes colorless when you react potassium permanganate with aromatic aldehydes or ketones. In this tube A, we had benzaldehyde. In this tube A, we had benzaldehyde. And initially, upon adding acidified potassium permanganate, this was the color of potassium permanganate. But after heating it up, it turned colorless. And in tube B, we had acetophenone. In tube B, we had acetophenone, and upon addition of acidified potassium permanganate, this was the color that the tube appeared. But after heating it for a while, we saw that the color of potassium permanganate disappeared because potassium permanganate got converted into, or permanganate ions got converted into Mn2+ ions, which is almost colorless. When potassium permanganate is acidified, it acts as an oxidizing agent. When it is acting as an oxidizing agent, the aromatic aldehydes and aromatic ketones get converted to their carboxylic acid. When it comes to aliphatic aldehydes and aliphatic ketones, we saw the aliphatic aldehydes react well with acidified potassium permanganate, allowing it to get oxidized. So we can see here we have acetaldehyde that have gotten oxidized to acetic acid or ethanoic acid. And in doing so, potassium permanganate or the permanganate ions got converted into Mn2+, which were colorless. But aliphatic ketones do not show a reaction with acidified potassium permanganate. So therefore, we can come to the conclusion that with acidified potassium permanganate, aliphatic ketones cannot be oxidized. And the benzaldehyde we had over here got converted into benzoic acid. You can see a white color precipitate forming here because benzoic acid is insoluble in water, and you can see a tiny white color precipitate being formed here. So this fine benzoic acid precipitate appears to be a cloudy solution because these fine particles of benzoic acid is suspended in this area. Here again we can see a slight cloudiness of this mixture as well. What we have here is acetophenone after it has taken part in a reaction with acidified potassium permanganate. So acidified potassium permanganate was able to convert acetophenone, an aromatic ketone, into its carboxylic acid, which is benzoic acid. You can see again cloudiness here That is due to the conversion of acetophenone into benzoic acid, which is insoluble in water, which results in formation of a white color precipitate due to being insoluble in water. In summary, students, when you're trying to react aldehydes and ketones with acidified potassium permanganate, the observations we had were aliphatic aldehydes will react with acidified potassium permanganate. Aliphatic ketones do not react with acidified potassium permanganate. Aromatic aldehydes and aromatic ketones both do react. Both of them do react with acidified potassium permanganate. That is a summary of the reactions that we see of the carbonyl compounds with acidified potassium permanganate. Let's move on to another oxidizing agent, that is acidified dichromate solution. In this part of our practical, we will see how acidified potassium dichromate, we can see this orange color solution here. We are going to see how aldehydes and ketones react with acidified potassium dichromate. Like in our previous examples, we will be taking a look at aliphatic carbonyl compounds and aromatic carbonyl compounds separately. We have acetaldehyde as our aliphatic aldehyde. We have 2-propanone as our aliphatic ketone. We have benzaldehyde as our aromatic aldehyde, and as our aromatic ketone we have acetophenone. Right. So first of all, let's start to add acidified potassium dichromate into our aliphatic aldehyde. So we have our aliphatic aldehyde here, acetaldehyde, also known as ethanol. We'll take a test tube labeled A and place some acetaldehyde into this test tube. And now we will take our acidified potassium dichromate and add a small amount of acidified potassium dichromate into this. And let's observe what happens to the color of the solution. Upon addition of acidified potassium dichromate, you can see the color of the solution gradually starts to change. Earlier on, acidified potassium dichromate had an orange color. You can see while you wait, it turns into a green color. Now it is completely green. The solution is completely green now. The reason for this is that acidified potassium dichromate is also a good oxidizing agent. So it can oxidize the acetaldehyde into acetic acid, or in other words, ethanol will be oxidized into ethanoic acid. So when this is happening, the dichromate ions present in the medium are the responsible species for this orange color in the dichromate solution. So the orange color dichromate ion converts into chromium ions, or Cr3 plus ions. As we have seen earlier, chromium ions are green in color. A chromium ion solution is going to be green in color. That is why you observe a green color in this medium. Let's add a little bit more to see a very clear green color. Now you can see as soon as I add a little bit of acidified potassium dichromate, it turns into orange again, and gradually you can see the orange color turns to a green color. Now it is green in color. This is due to the formation of chromium 3 plus aqueous ion solution. We saw that aliphatic aldehyde reacts with acidified potassium dichromate. Let's move into our aliphatic ketone. We have 2-propanone, or in other words, we have acetone here. Let's take a small amount of acetone into our test tube, labeled B. And to this acetone, we will add acidified potassium dichromate. Upon addition of acidified potassium dichromate, what are the observations you see? Do you see a color change? To observe this very closely, to another test tube, let's take a little bit of acidified potassium dichromate. Now, we can compare the colors of acidified potassium dichromate along with acetone treated with acidified potassium dichromate. So the color has not changed. Only thing that you see here is a small dilution of the color. But to make sure that we are not seeing a color change, not because of how slow the reaction is happening, we are going to place both of these test tubes in a water bath. So if there's a very slow reaction happening in this test tube B, where we have our acetone mixed with acidified potassium dichromate, we want to make sure that we provide it with enough heat for the reaction to take place faster. But if there is no reaction taking place, you will see that this color persists without it changing color. We now place both our control and our reaction mixture in the water bath. We will let it stay there for a while. Students, now we have allowed the 2 test tubes to heat up in a water bath for a while now. Let's see what the observations are. Over here, we have the 2 test tubes. In test tube B, we have our acetone mixed with acidified potassium dichromate, and on my left hand, what I have here is just a sample of acidified potassium dichromate. Upon heating, both of them did not change color. So let's put aside the control and focus on our acetone containing test tube. So in the presence of acidified potassium dichromate, acetone did not have any reaction. That is why the color of the potassium dichromate persisted. Right? So this is an indication that aliphatic ketones do not react with acidified potassium dichromate. So there is no observation when you are reacting acidified potassium dichromate with aliphatic ketones. Now, let's move on to aromatic aldehydes and aromatic ketones. We have benzaldehyde as our aromatic aldehyde. We'll take a small amount of it into our test tube A. And Into our test tube B, we will take our aromatic ketone, which is acetophenone. We will take a small amount of acetophenone and add it to our test tube B. And now, to both of these test tubes, let's add a small amount of acidified potassium dichromate to see if the color of acidified potassium dichromate will change into a green color like in the acetaldehyde reaction. So we have our potassium dichromate, acidified potassium dichromate solution over here. We'll add small amounts of it into both test tube A and test tube B. As you can see, upon addition of acidified potassium dichromate to both of these test tubes, we cannot necessarily see a color change. This could be due to the reactions happening very slowly. So what we are going to do is we are going to heat these test tubes up. After shaking each of these test tubes a while, I will be heating these two test tubes up to see if the color of these acidified potassium dichromate solutions will change over time. Let's place them both in a water bath and heat them up for a while. When we provide these two mixtures some heat, the reaction will happen faster, and then if there is going to be a color change, we will be able to observe it faster due to providing it heat. Let's see after a while whether the color has changed. Students, we have allowed the two test tubes to be heated in the water bath for a while now. Let's take them out. You can see here the two test tubes now have changed in color. Let's compare one by one. Initially, when we added acidified potassium dichromate, the acidified potassium dichromate had this orange color. So on this bottom layer, the color that we observed was this orange color. Now after a while, you can see when we added benzaldehyde and acidified potassium dichromate and mixed the two together, and we allowed it to react under elevated temperatures. So we heated this mixture up and we saw the reaction was happening a little bit faster than at room temperature, and the potassium dichromate color, or the dichromate ions color, the orange color, disappeared and it turned into a green color. And at the same time, there's a little bit of a cloudy nature. That is due to the fact that benzaldehyde got oxidized to benzoic acid, which is a white color precipitate because it is not soluble in water. So the white color precipitate that you see here over on the top layer, as well as you can't necessarily see the white color precipitate here on the bottom layer. However, we have formed a white color precipitate, which is benzoic acid, insoluble in water, as well as the dichromate ion has converted into chromium 3+ ion. So the dichromate ion has actually reduced, whereas the benzaldehyde has oxidized into benzoic acid. Now let's see what happened to acetophenone when it was reacted with acidified potassium dichromate. You can see here, when acetophenone was reacted with potassium dichromate, the color of the dichromate ions have turned to a green color. Dichromate ions are orange in color due to dichromate ions reducing to chromium 3 plus, we can see a green color solution being formed here. And over here, we can see a precipitate being formed. Acetophenone, when oxidized in the presence of acidified potassium dichromate, it will convert into benzoic acid. Benzoic acid is insoluble in water. That is why you can see a cloudy nature in this green color solution as well. And over here, we can see a white color precipitate formed, that is benzoic acid, insoluble in water. Now, let's take a look at our summary. Initially, we reacted acetaldehyde with potassium dichromate, and we can see in the presence of acidified potassium dichromate, acetaldehyde got oxidized into acetic acid. So, in this oxidation, the dichromate ion got reduced to chromium 3 plus. So, what you see here is the color of the chromium 3 plus aqueous ions that are present in the medium. So, it is green in color, as chromium 3 plus aqueous ions are green in color. So, in the presence of acidified potassium dichromate, acetaldehyde gets oxidized into acetic acid. And then we took another aliphatic ketone, which is acetone or 2-propanone. In the presence of acidified potassium dichromate, acetone did not show any reaction. Acetone did not react with acidified potassium dichromate, so therefore there was no color change. We can still see the color of acidified potassium dichromate persisting in that test tube. And to benzaldehyde, when we added acidified potassium dichromate and heated it, we got a mixture of two layers. You can see in the aqueous layer, the color of potassium dichromate has changed from orange to green. This is due to the dichromate ion reducing to chromium 3 plus while oxidizing the benzaldehyde into benzoic acid. So, the cloudiness is due to the white color precipitate that is formed, benzoic acid, which is insoluble in water. When we reacted acetophenone with acidified potassium dichromate, we saw the same observation. The aqueous layer, which was orange in color due to the presence of acidified potassium dichromate, got converted into a different color, which is green, due to dichromate ions reducing into chromium 3 plus ions. And while this reduction is happening, the acetophenone got oxidized into benzoic acid. And again, due to benzoic acid being insoluble in water, you can see white color precipitate present here and of benzoic acid. With that, we come to an end of the reactions that you see with acidified potassium dichromate with aldehydes and ketones. Now, we plan to move on to our next test, which is the reactions that you see with tolerance reagent. So, aldehydes and ketones, how they react with the tolerance reagent can now be tested. In this section of our practical, we will focus on how these aldehydes and ketones react with the tolerance reagent. So, what we have here is our tolerance reagent. The way that we can prepare this is mentioned in our practical book as well. But just to go over the method, again I will mention it here. We will take silver nitrate solution, and to it we will add a few drops of sodium hydroxide. Upon addition of sodium hydroxide, you will see a precipitate being formed, and to that precipitate you have to keep adding ammonia until that precipitate dissolves. The resultant solution is referred to as ammoniacal silver nitrate. Another name for that is tolerance reagent. So what we have here is our tolerance reagent. So just like in the previous experiments, we will take our aliphatic aldehyde and aliphatic ketone and add tolerance reagent and see what happens. So I will take aliphatic aldehyde, which is ethanol or acetaldehyde. Now I have a test tube labeled A here. To that test tube, I will take a small amount of ethanol. Now you can see I have taken a small amount of ethanol here. To that, I will add tolerance reagent. This reaction is very slow and will not take place clearly at room temperature, so we will have to heat it up. But first, let's set it aside for a while. And we'll take another test tube labeled B, and to this we will add our aliphatic ketone. And to our aliphatic ketone, we'll add small amount of tolerance reagent as well. And now, in our test tube A, we have our aldehyde, which is acetaldehyde, mixed with our tolerance reagent. In our test tube B, we have our ketone, aliphatic ketone, acetone, mixed with tolerance reagent. Let's place them both in a water bath and leave it there for a while to see if they answer to the tolerance reagent. While they warm up, I will explain to you what happens here. When you add tolerance reagent onto aldehydes, aldehydes get oxidized into carboxylic acids, and tolerance reagent have silver ions that gets reduced into silver solid. So this silver solid that is formed gets coated on the interior walls of the test tube, and the test tube appears to be a silver mirror. Due to deposition of silver solid on the interior walls of the test tube is going to appear as a silver mirror. So we will leave test tubes for a while. We know in the test tube B, we are having a ketone. Ketones do not answer to the tolerance reagent, so you will not see a silver mirror being formed with ketones. However, test tube A should end up forming a silver mirror as we have an aldehyde in the test tube along with our tolerance reagent. When we heat it up for a duration, we should get the result of seeing a silver mirror. Students, we have allowed the two test tubes to heat up for a small duration, right? So after about 5 minutes, now we are going to observe the changes of the two test tubes. So let's take the two test tubes. You can see here the test tube A. The test tube A has formed a silver mirror, but the contents in test tube B have not formed a silver mirror. So contents in test tube B has not formed a silver mirror because we had a ketone in there. Ketones do not answer to our tolerance reagent test. So let me show you the silver mirror that is formed very clearly. Let me remove the contents of this test tube into another beaker. And now we can very clearly see the silver mirror that is formed when we reacted an aldehyde, aliphatic aldehyde, with the tolerance reagent. So what you see here is a silver mirror that is formed when acetaldehyde or ethanol was reacted with the tolerance reagent and was heated up for a while. You can see the interior walls, the entire interior walls of this test tube is now coated with silver, and the test tube appears to be a silver mirror. So this is the silver mirror test. This is a positive answer to the silver mirror test. And over here in the test tube B, what you see is a negative answer, which means it does not answer to the silver mirror test. So ketones do not answer to the silver mirror test. Now let's move on to the second set of experiments here, that is the reaction of aromatic aldehydes and aromatic ketones with tolerance reagent. So like in the first experiment here, let's add our aromatic aldehyde that we have here, benzaldehyde, into our test tube A. We will take a generous amount of the aldehyde to make sure that we see a really good silver mirror when it is formed. So we have taken benzaldehyde into test tube A, and into our test tube B, let's add acetophenone, our aromatic ketone. We will take small amount of acetophenone into this test tube, and we will place it here. So in our test tube A, we have benzaldehyde, and in our test tube B, we have acetophenone. Now to both of those test tubes, let's add our tolerance reagent. We have added our tolerance reagent here. Into test tube B as well, we will add our tolerance reagent. As you can see, now we have added to both the test tube the tolerance reagent, and to test tube A we have added our aromatic aldehyde, and in test tube B we have our aromatic ketone. Now we will place them in a water bath for the reaction to go to completion. We will leave it there for a while and come back and take a look at the observations. Students, we are here after a few minutes to observe the changes that has taken place when we place the two tubes on a water bath. So let's take tube A and tube B out of the water bath. You can see here tube A and tube B are different now. As you can see, tube A has formed a silver mirror, but tube B has not formed a silver mirror. As you can see, the test tube A containing the aromatic aldehyde has answered positively to our silver mirror test, forming a silver mirror inside the test tube. and the aromatic ketone containing test tube B, has not answered positively to the silver mirror test. So we'll set it aside for a while and let me remove the contents of this test tube. Now you can very clearly see how the interior walls of the test tube A is coated with silver. Again, as I mentioned before, when we carry out the silver mirror test with the help of tolerance reagent, the silver plus ions in the tolerance reagent gets converted into silver solid. While this reduction is taking place, the aldehyde that was present inside this mixture gets converted into a carboxylic acid. So the aromatic aldehyde we had, which is benzaldehyde, gets converted into benzoic acid, and silver plus ions got converted into silver solid, and this silver solid got deposited onto the interior walls of this test tube, creating a silver mirror. Let's move on to the summary of this experiment. In this experiment, we looked at aliphatic aldehyde, which answered positively to the tolerance reagent test, forming a silver mirror. Aliphatic ketones did not answer positively to our silver mirror test with tolerance reagent. And then we took a look at aromatic aldehyde. Aromatic aldehyde gave a positive result for our tolerance reagent test, forming a silver mirror, as you can see here. Aromatic ketones did not answer positively to our silver mirror test. So in conclusion, we can see all the aldehydes, regardless of whether it is an aromatic aldehyde or an aliphatic aldehyde, it will answer positively to our silver mirror test. Ketones will answer negatively. It will not provide you a silver mirror when you react a ketone with tolerance reagent. With that, let's move on to the final section of this practical, which is the reaction of aldehydes and ketones with Fehling's solution. In this final part of our practical, we will be taking a look at how aldehydes and ketones react with Fehling's solution. Here we have our Fehling's solution. This Fehling's solution is prepared by mixing equal amounts of Fehling's A and Fehling's B. So we have two solutions that are named Fehling's A and Fehling's B. We mix equal quantities of these two solutions and prepare our final Fehling solution. Fehling's A contain copper 2 sulfate or copper sulfate, CuSO4. So that is why Fehling's A solution is going to be a blue color. And then we have Fehling's B made with potassium sodium tartarate. So when you mix the two up, we get our final Fehling solution, which we have here. Fehling solution will react with aldehydes, especially aliphatic aldehydes, and form a brick red color precipitate. However, Fehling solutions do not react with ketones, and also it does not react with any aromatic aldehydes. So it only answers to aliphatic aldehydes. Aliphatic ketones, aromatic ketones, and aromatic aldehydes will not answer to our Fehling's test here. So let's move on and see if we can notice these observations. When we are doing this experiment, we will have to use a boiling tube, and we will be adding our Fehling's solution to each of these aldehydes and ketones we have in front of us, and we will be heating it up with the help of a Bunsen burner. So since we are going to heat it up with the help of a Bunsen burner, I'll be using this test tube holder to make sure that heat does not transfer to my fingers while holding boiling tube. Let's take our aliphatic aldehyde ethanol into our boiling tube. So we have ethanol or acetaldehyde, the common name for ethanol. We will add a small amount of ethanol into our boiling tube. And now we will take our Fehling's solution and add a small amount of Fehling's solution into this boiling tube. So as you can see, upon addition of Fehling's solution into this boiling tube, when it is added with ethanol, the resultant solution is still blue in color. The reason for this is this reaction is happening very slowly, so we will have to provide heat for this reaction to take place. So now let's heat this boiling tube. When you are heating a solution like this, please make sure to aim the opening of the boiling tube away from you. If any spilling or splashing is to occur, at that point, you make sure you are safe by aiming the boiling tube away from you. Now you can see when I heat it up, gradually the color of this solution changes little by little, and we are hoping to obtain a brick red color precipitate. Already it shows a slight orange color. If we heat it long enough, it will finally produce the brick red color precipitate that is characteristic of this Fehling's test. Students, you can observe here the formation of a brick red precipitate. Over here, although it appears as if it is a solution, what you see here is a formation of a brick red color precipitate. So what happens here is, in the initial solution of Fehling's, we had copper 2 plus ions, and when it is reacting with the aldehyde, aldehyde oxidizes to a carboxylic acid. So we had ethanol, it oxidized to ethanoic acid. So what happens here is copper 2 plus ions got reduced to copper 1 plus and formed cuprous oxide, Cu2O, cuprous oxide or copper 1 oxide. So what you see here as a precipitate is a brick red color cuprous oxide. Let's move on to the next experiment. Now we will take an aliphatic ketone, which is acetone. We have acetone as our aliphatic ketone, and we will react it with Fehling's solution. We already know that the Fehling's solution will not answer to aliphatic ketones or aromatic ketones for that matter. It will not answer to aromatic aldehydes as well. So the only positive test we are going to see for the rest of this experiment is going to be our aliphatic aldehyde that we saw earlier. But still, let's go on with our experiment and see if there's any color change that we can observe. Now let's heat the reaction mixture containing our aliphatic ketone and the Fehling's solution. As you can see, upon heating it, we are not seeing any change. This is because the ketones cannot oxidize into carboxylic acids. Aliphatic ketones cannot oxidize into carboxylic acids in the presence of an oxidizing agent like Fehling's solution. So we can see the solution is starting to boil, but still no color change. This indicates that in the presence of Fehling's solution, aliphatic ketones do not have a reaction. Aliphatic ketones cannot convert into carboxylic acids with the help of Fehling's solution, so therefore no reaction will take place. We will now safely remove this into our test tube rack. And we will move on to our next experiment, which is reacting Fehling's solution with an aromatic aldehyde. Now we have our aromatic aldehyde, benzaldehyde. Let's take benzaldehyde and see what happens when we add Fehling's. We'll take a small amount of benzaldehyde into a boiling tube. And to that, we will add a small amount of Fehling's reagent. We'll mix it together as much as we possibly can. And let's observe if there's going to be a color change when you heat this solution up. So now, as you can see, benzaldehyde is not soluble in water, and Fehling's solution is mostly organic, and Fehling's solution is mostly aqueous. So you can see there's somewhat of a layer separation there. When you heat it, as in the previous experiment with the ketone, the aromatic aldehyde also does not show a color change. As you can see, it boils off, sometimes shoots out as well, so you have to be very careful pointing it away from you. And when you're pointing these things away from you, please make sure not to point it at anyone else as well. Because when this boils off, it might splash out of the opening of the boiling tube, which might result in a burn injury in someone in front of you. So as you can see, upon heating it until some of the organic layer boils off, we saw no color change. Still, the blue color of the Fehling's solution persists. This is an indication that aromatic aldehyde did not have any reaction with the Fehling's solution. If the Fehling's solution reacted with it, it will end up forming copper 1 oxide or cuprous oxide, which is a brick red color precipitate. We did not see that here, indicating that the Fehling's solution did not react with the aromatic aldehyde we had here, benzaldehyde. Let's move on to the aromatic ketone. The aromatic ketone we have is acetophenone. We have acetophenone here. Let's take a small amount of acetophenone onto our boiling tube. And to acetophenone, let's add a small amount of Fehling's solution. Again, as you can see, there will be layer separation because acetophenone will not dissolve in Fehling's solution, which is mostly aqueous, and acetophenol is an organic nonpolar layer which will not dissolve in the Fehling's solution. But we will mix it up as best we can. And then we'll heat it up with the help of a Bunsen burner.
if there is any reaction, we will see a color change in the phthalenes solution layer. When you are heating it up, please be very careful. These are all organic solvents. They will quickly evaporate as well as quickly boil off. It could result in a splash hazard. So you can see the organic layer, although it's boiling, still there is no color change. Still there is no color change, indicating that the phthalenes solution was not capable of oxidizing the aromatic ketone. So the aromatic ketone did not get oxidized into a carboxylic acid. So therefore, the phthalenes solution retained its color that comes from copper 2+ ions. So having this blue color indicates that in the presence of phthalenes solution, aromatic ketones, in this case we specifically took acetophenone. Acetophenone does not react with the phthalenes solution. Students, let's move on to our summary, and this is our final experiment in the experiment number 27 practical series. So in this final step, we observed that with phthalenes solution, only aliphatic aldehydes give positive results and form brick red color precipitate. Only aliphatic aldehydes will form brick red color precipitate in the presence of phthalenes solution. Aliphatic ketones did not change the color of the phthalenes solution because aliphatic ketones cannot get oxidized in the presence of phthalenes solution. So you can see the blue color of the phthalenes solution actually persisted upon heating as well. Then we took benzaldehyde, our aromatic aldehyde. Even that did not react with phthalenes solution. The color of the phthalenes solution did not disappear due to phthalenes solution not reacting with aromatic aldehydes. Finally, we looked at aromatic ketones. Even that did not turn the color of the phthalenes solution into a brick red color, indicating it did not react with the aromatic ketones as well. So only aliphatic aldehydes answer to phthalenes solution. Aromatic ketones, aromatic aldehydes, and aliphatic ketones do not answer to phthalenes solution. With that, we finish the practical number 27, and now let's move on to important theory parts related to this practical, as well as some questions related to this practical.
GCE Advanced Level Chemistry Practical Series Experiment number 27, Test for Aldehydes and Ketones. Students, we discussed the theory parts revolving around this experiment, and then we went into the lab and conducted this experiment, and now we are going to be discussing some questions revolving around the theory knowledge of this experiment. Let's take a look at the first question. First question, it says, when 1 mole of compound named Y contains carbon, hydrogen and oxygen, undergoes complete combustion, it produces 4 moles of carbon dioxide and 4 moles of water. So from 1 mole of Y, it produces 4 moles of carbon dioxide and 4 moles of water. Y does not produce a precipitate with 2,4-dinitrophenyl hydrazine. So what is 2,4-dinitrophenyl hydrazine? 2,4-dinitrophenyl hydrazine is Brady's reagent. Why do we use Brady's reagent? It is normally used to identify the presence of carbonyl compounds, which is aldehydes and ketones. However, it reacts with metallic sodium to produce a colorless gas. So students, what are the reactions that are normally seen with metallic sodium when it comes to organic compounds that contain carbon, hydrogen and oxygen? There are few compounds that contain carbon and hydrogen and oxygen that are capable of reacting with metallic sodium. And those compounds are alcohols, phenols, and carboxylic acids. So you have to keep those in mind when talking about or when you are looking into a question like this. Y shows cis-trans isomerism, or in other words, geometrical isomerism, and has a relative molecular mass of 72. And they're asking us to give the possible structures of Y and write their UPSC names. Now students, when it comes to a question like this, you have to understand first that there is a compound that is given to you by the name of Y, and it reacts with oxygen to form carbon dioxide and water. So your key understanding when it comes to a question like this should be that the carbons in the carbon dioxide and the hydrogens in water came from nothing else other than the compound Y. So when it comes to the products that you see here, in the products, the carbons in the product and the hydrogens in the product came from only Y. But when it comes to oxygen, oxygen could have come from Y as well as the atmospheric oxygen we use to combust Y. So therefore, when I say, or when the question says 1 mole of Y forms 4 moles of carbon dioxide and 4 water molecules, you have to understand that 1 mole of Y produce 4 carbon dioxide, meaning the 4 carbon atoms that you see over here came from 1 Y, or 4 moles of these carbon atoms came from 1 mole of Y. So 1 mole of Y contains 4 moles of carbon atoms, or in other words, 1 molecule of Y contains 4 carbon atoms. So with that information, we can actually write down half of its formula. Carbon number in the Y compound, the carbon number would be 4. When it comes to the water molecule that we have here, right? We have hydrogen. From where did this hydrogen come from? Hydrogen also came only from compound Y. So 1 mole of Y forms 4 moles of water, indicating that these 8 hydrogen atoms came from 1 molecule of Y. So hydrogen number of this Y compound is 8. 1 mole of Y produce 4 water molecules, indicating that the 8 hydrogen atoms in the water molecule came from 1 molecule of Y, or 1 mole of Y actually had 8 hydrogen moles, or hydrogen atom moles. So students, that is why we have written C4H8 here, because whatever the number of hydrogen atoms that we see over here and the number of carbon atoms that we see over here came from nowhere else other than Y. We can't say the same about oxygen, so finding out the value of or number of oxygen atoms in the molecule is a bit tricky. Why? Because oxygen can come from, or oxygen atoms that you see here on the product side can come from atmospheric oxygen and the number of oxygen atoms in Y. So therefore, to find out the number of oxygen atoms in the compound Y, we can take a look at the relative molecular mass of Y, which is 72. So currently we know that Y contains 4 carbon and 8 hydrogens. So 4 carbon atoms bring in a mass of 48. And we know when it comes to hydrogens, there are 8 hydrogens. Each hydrogen has a mass of 1, relative atomic mass of 1, so therefore it brings in a mass of 8, altogether 56. So this C4H8 part is responsible for 56 of the overall relative molecular mass, and the overall relative molecular mass is 72. So this section should be the rest. So if you take 72, and take off 56, you are left with 16. So how many oxygen atoms can bring in a relative molecular mass of 16? What is the relative atomic mass of oxygen? 16 itself. So basically, how many oxygen atoms are there? 16 divided by 16 is going to be 1. So indicating that there is just one oxygen atom here. So the actual formula of Y would be C4H8O1. We wouldn't write the 1, so the Y compound has the formula C4H8O. So this is the formula of Y. Now, after taking a look at the formula, we have to take a look at the isomers that are available when it comes to this particular compound. So let's take a look at the structure of C4H8O. So if you write 4 carbons, or before we go into that, we have to analyze what type of compound this is before we go into writing the structure. We need to analyze what type of compound this could be. So now we know the molecular formula. So now we have to analyze what kind of compound would react with metallic sodium but wouldn't give a precipitate with 2,4-DNP, which is Brady's reagent. So if it doesn't show reactions Brady's, indicates that this is not an aldehyde or a ketone. But at the same time, this reacts with metallic sodium, indicating it has acidic properties. So could it be a phenol? Could it be phenol? Could it be a phenol? Now phenol contains 6 carbon atoms. We have only 4 here. Definitely not phenol. What about carboxylic acids? Can it be a carboxylic acid? Because carboxylic acids react with metallic sodium. Phenols react with metallic sodium. Carboxylic acids react with metallic sodium. Can it be a carboxylic acid? No. Why not? Because it has 2 oxygens. When it comes to our molecular formula, it contains only 1 oxygen. So therefore, this is also not correct. And then we have after these 2, the weakest acidic compound that we can think of is alcohols. Does alcohols react with metallic sodium? Yes. Does it conform to this molecular formula? Yes, we can. By looking at the number of oxygens, you can see, yes, there's only 1 oxygen when it comes to alcohols. Over here as well, we can see 1 oxygen. So therefore, this could be an alcohol. So keeping that in mind, we can now draw the structure of a alcohol with 4 carbon atoms. Now students, if you draw an alcohol like this, I want you to take a look at this and see what the problem is. The number of carbons are alright, number of oxygen is okay, but number of hydrogens are incorrect. There is altogether 10 hydrogens. But when it comes to our formula that we actually discovered earlier or found out earlier, it had only 8. So can this be the answer? No. However, we can fix this issue very easily by adding a double bond. As you know, when you're adding a double bond, the hydrogen number will go down by 2. So if you add a double bond here, CH2 double bond, CH, CH2, CH2, OH. Now the number of hydrogens, carbons and oxygens are exactly the same as given in the molecular formula, which is C4H8O. We have 4 carbons, 8 hydrogens and 1 oxygen here. So after identifying what the structure could be for compound Y, now we have to take a look at the cis-trans isomers that they can form, because the question says the compound Y has geometrical isomerism, which is cis-trans isomers. So we have to first of all write them down and name their IUPAC names. So this particular compound cannot show cis-trans isomerism. Why? When you have 2 similar groups attached to a carbon that contains the double bond, you can't show cis-trans isomerism. So therefore, this compound is not the answer to Y. Can we, while we are discussing the possible structures, can we include an OH group? Can we include an OH group on a carbon that is forming a double bond? So you have these 2 carbons are contributing to form the double bond, and on one of those carbons you have an OH group. Can this be formed? The answer for that is also no. You can't form this as well. That is because what you form here when you attach an OH group to a carbon-carbon double bond, or to a carbon that is forming a double bond, is an enol. And enols are unstable. Enols will actually rapidly undergo rearrangement to form either aldehydes or a ketone. Majority of the time it will be ketones. So when it comes to enols, since they are unstable, when you are asked to write the cis-trans isomers of compound Y, you can't include enols. So that limits our options. This can't be the answer. When you are having a carbon-carbon double bond, you can't have an OH group attached to one of the carbons contributing to form the carbon-carbon double bond. So then, since we have limited options at this point, we can actually move the carbon-carbon double bond from the first carbon to the second carbon and see if that helps. So when you move it to the second position, of course, it helps. Now you can see each of the carbons that is forming the double bond contains 2 different groups. So we can now draw our cis and trans isomers. We can see to one of the carbons that are forming the double bond, there's a CH3 group and a hydrogen group, and to the second carbon forming the carbon-carbon double bond, we have a CH2 OH group and a hydrogen group. And then after drawing this first structure, we can rotate, or we can actually flip these groups and get to this particular isomer. Right. So we can see we have formed the 2 isomers. So these are the only 2 isomers that you will be able to draw, because all the other isomers either does not show cis-trans isomerism or is going to be unstable due to formation of a enol. Now students, we have to write the name of this compound. So let's start numbering this compound. We will give priority to the carbon that contains the OH group. So carbon number 1, 2, 3, and 4. So this contains 4 carbons. We can start the name with but. And when it comes to the second carbon, we can see a double bond. So we can write but 2 ene, en only. The last E is not going to be present here because this is an alcohol, right? And the alcohol group is connected to the first carbon. So we write in 1 ol. So the answer is but 2 in 1 ol. But 2 in 1 ol. That is the name of this compound. However, that compound has 2 isomers, cis and the trans isomer. So what is the name of this particular isomer? You can see similar groups are present on the same side. So therefore, this is your cis isomer. We have our cis but 2 in 1 ol. 2 in 1 ol. And then over here we have trans but 2 in 1 ol. Trans but 2 in 1 ol. You can see when it comes to the trans isomer, we have similar groups opposite one another across the double bond. So these are the names of these compounds. So this is the answer to the question that is asked. Compound Y has cis-trans isomers. One is cis-but 2 in 1 ol. The other one is 2-but 2 in 1 ol. So with that, we can move on to the next question. So the first question was this. Now we can move on to the second question. In the second question, they're asking us to identify 2 compounds separately. And they're asking us, how can the below pairs of compounds be separately identified with the use of chemical reactions? We have propene and 2-butyne. Propene and 2-butyne. First of all, let's draw propene and 2-butyne. Propene contains 3 carbons, CH3, C double bonded carbon here, CH, CH2, this is propene. And then we have 2-butyne, CH3, C triple bonded carbon, and another CH3 group will be there. So we have 4 carbons here and a triple bond in the middle. So they're asking us to identify these 2 separately. So you can actually identify these 2 separately by doing the following chemical test. We can add HgSO4 and dilute H2SO4. HgSO4 and dilute H2SO4 will go on to produce these 2 compounds. Now, in the presence of this reagent, the first compound will turn into an alcohol. And the second, you know very well, when it comes to this type of alkyne, when you react with mercury sulfate and dilute sulfuric acid, it will form a ketone. So after forming these 2 products, we can separate them from the reaction mixture. And after separating them from the reaction mixture, we can add to them Brady's reagent 2,4 or 2,4-DNP, dinitrophenylhydrazine. We can do the same over here. DNP. Right, students. So when you add 2,4-DNP to both of them, when it comes to an alcohol, there will be no observation. You would not necessarily observe any color change, right? So when it comes to 2,4-DNP reacted with a secondary alcohol like this, that's going to be no precipitate formed. But when it comes to a ketone reacting with 2,4-DNP, you can see a bright orange or a yellow orange. Bright or a yellow orange precipitate will be formed. So students, this is how you can actually identify these two compounds separately through chemical test, right? First, you include mercury sulfate, dilute sulfuric acid, and you can include water here as well. And then you convert the first compound, which is propene, into an alcohol, a secondary alcohol. And when it comes to 2-butine, it will get converted into a ketone. And ketones answer to Brady's reagent, 2,4-DNP. So therefore, it will give you a yellow-orange or a bright orange color precipitate in the presence of 2,4-DNP, but the alcohol will not. So therefore, we can use this test to identify these two compounds separately. Right, students. So with that, let's move on to the second set of compounds. We have formaldehyde and benzaldehyde. So this is a continuation from the previous question. They're asking us to identify these two compounds separately. Formaldehyde and benzaldehyde. So formaldehyde is the simplest aldehyde you can find. It's going to be this aldehyde. And we have benzaldehyde. Aldehyde with an aromatic ring. So when it comes to these two aldehydes, how do you identify these two aldehydes separately? As you know, there are certain chemical reactions that will only answer to aliphatic aldehydes, but not to aromatic aldehydes. Brady's reagent, of course, will react with both of them and will produce a bright orange or yellow-orange precipitate. But when it comes to things like Phalene's solution, will Phalene's solution answer to both of them? No. When it comes to Phalene's solution will only answer to the aliphatic aldehyde that we have here. It will only answer to the aliphatic aldehyde we have here and not to the aromatic aldehyde. So let's take a look at some tests that we can use to separately identify these two. We can use, bear with me a second, students. We can use Phalene's solution. Phalene's solution will give you a brick red color precipitate with formaldehyde. So when you add Phalene's and warm it in a water bath, within about 5 minutes or so, you will observe a brick red precipitate. But when it comes to acetaldehyde, or not acetaldehyde, when it comes to benzaldehyde, you will not necessarily see this brick red color precipitate forming. It will take a long time, as Fehling's reagent doesn't necessarily react very fast with benzaldehyde. It's extremely slow. So therefore, we can say you will not observe the formation of the brick red precipitate. So that can be used to separately identify the two compounds. Apart from that, students, we can actually use another test, which is a test like reacting both of them with acidified potassium permanganate or with acidified potassium dichromate. So if you are right now thinking, doesn't both of them react with acidified potassium permanganate? Yes, both of them will react with these oxidizing agents. Acidified potassium permanganate and acidified potassium dichromate will react with formaldehyde as well as benzaldehyde. So then, how can we separately identify these two? When it comes to formaldehyde, if you are talking only about one oxidizing agent, let's take potassium permanganate. So when you take acidified potassium permanganate and react with formaldehyde, it will decolorize potassium permanganate. It will go from purple to colorless. But when it comes to benzaldehyde, apart from decolorizing the potassium permanganate solution, benzaldehyde gets converted into benzoic acid, which is insoluble in water, which is going to be formed as a white color precipitate. So therefore, students, due to the formation of white color precipitate, you can separately identify these two compounds with the use of oxidizing agents such as acidified potassium permanganate or acidified potassium dichromate. Apart from the obvious color change that you are aware of, there's going to be a precipitate formed when it comes to the aromatic aldehyde. So let's take a look at that. You have acidified KMNO4, and when you react it with formaldehyde, you're going to be forming formic acid, which is going to be soluble in water. But if you react it further, it can turn into carbon dioxide. Right, so apart from forming water-soluble, colorless formic acid, you're going to see the color change from purple to colorless. Purple color, decolorized. Purple color will get decolorized. When it comes to benzaldehyde will form benzoic acid. Benzaldehyde will form benzoic acid, which is water insoluble, which is going to be present as a white color precipitate. So again, the same observation is there. Purple color, decolorized, and white precipitate. Apart from that, a white precipitate will be formed. So students, this can be used to identify these two compounds separately. So you can ask yourselves, what is the observation when it comes to potassium dichromate, acidified potassium dichromate? Acidified potassium dichromate is orange in color. When it oxidizes an aldehyde, acidified potassium dichromate turns into chromium 3+, so therefore orange color turns into a green color. So the color change will be orange to green. Here also you will have orange to green color change. However, on the second column, as you can see, as benzoic acid gets formed, you will have a white color precipitate formed as well. So that is why when it comes to the question that we have over here, you can use acidified potassium permanganate or acidified potassium dichromate also to identify between these two compounds. Right. With that, let's move on to the next question. Right. Given below are isomers that can be seen for the molecular formula C5H10O. Give the names of the following isomers. So they're asking us to give the names of the following isomers. We have the very first isomer here. And you can see there are altogether 5 carbons. 1, 2, 3, 4, 5. And this is a ketone. We can write the name as pentane, and the carbonyl carbon is found on the 3rd position. We can write pentane 3-one or 3-pentanone. That is also correct. 3-pentanone can also be written. Right? Both of these are correct. So the IUPAC name of this is pentane 3-one. Next one we have here, give the names of this particular compound, B compound. You can see apart from the main carbon chain, so this is our main carbon chain. There's another group attached to the main carbon chain. So that is a methyl group. We always have to give priority to the carbonyl compound. So when you are numbering this carbon chain, you can start numbering from here 1, 2, 3, and 4. And on the 3rd position, you have a methyl group, and the carbonyl carbon is present on the 2nd position. So when it comes to this particular compound, since it has 4 carbons in the main carbon chain, and then there's a side chain which is a methyl group, we can start writing the name 3-methyl but 2-one. 3-methyl but 2-one or 3-methyl 2-butanone also is a correct answer. 3-methyl but 2-one is the name of this particular compound. And this, what we have right here, is not a ketone. In the previous 2 instances, what we had was ketones. Is this a ketone? No. This is a aldehyde. So therefore, when it comes to this particular compound, in the previous compound, just like that, we have 4 carbons here, and we are going to be giving the priority to the carbon with the aldehyde group. So that is going to be carbon number 1, 2, and this is 3 and 4. On the 3rd position, you have a methyl group. So we'll start with that. 3-methyl but. And when it comes to aldehydes, the aldehyde always is given the priority. So therefore, we don't have to necessarily mention it is 1-al, or we don't have to mention the location of the aldehyde group. So we can straight away move on to writing the name 3-methyl butanal. 3-methyl butanal. So when it comes to aldehydes, the name ends with Al. When it comes to ketones, of course, you know the name ends with One. Right? So since this is an aldehyde, the name ends with Al. So 3-methyl butanal would be your answer. Let's move on to the next question. How can you identify A and B separately with a single chemical reaction? How can you identify A and B separately with a single chemical reaction? So A is a ketone, which is pentane 3-one, and B is 3-methyl butane 2-one. So when it comes to A and B, we'll try to answer this question here where both the structures of A and B are present. This particular B compound contains this O or COCH3 group, which can be identified by a test that is known as the iodoform test. We can identify this by a test that is known as the iodoform test, you don't have a COCH3 group. Instead, we have a CH2 CH3 group over here, which cannot be identified by our iodoform test. So therefore, students, when it comes to this particular compound or these two compounds, the easiest way to identify those two is by using the iodoform test. But iodoform test is now removed from the syllabus. However, if you are interested to know what the iodoform test is going to, or how the iodoform test is going to give you the observation you want, I will discuss how it takes place here. So we have our iodoform test normally answers to ketones that contain this group mainly. So you can see that group is present here, and when you react a ketone like this with dilute sodium hydroxide and iodine, you get to these products. CH3, the main carbon chain doesn't necessarily chain, it is still a carbon chain. Actually in this case you can see we have 3 carbons leading up to the carbonyl carbon, so that part of the carbon chain actually doesn't change. But since then you can see this is no longer a ketone, instead it becomes a carboxylic acid, but due to the basic nature of the medium it forms this salt. Apart from that, you're going to be forming CHI3, which is iodoform, and this is going to be present as a yellow color precipitate. So if your ketone contains this COCH3 group that I have mentioned here, if you add sodium hydroxide and iodine, you will see the formation of a yellow color precipitate. So only compound B has this. Compound A, give me a second, that looks like this, will not answer to the iodoform test. Compound A will not answer to iodoform test, but compound B would. So students, this is how you can identify these two compounds separately. But if you want to identify it without the use of iodoform, that also can be done. Let's take a look at that. So this is A. This is A. And we have our B here. Now, if you react both of these with lithium aluminium hydride, in dry ether and add water to it later. So I will write the reaction here. Lithium aluminium hydride and then water. You will get to these products. This is one of the products that you form from A. When it comes to B, you will be forming this product. And after forming this, we have converted these two into alcohols. Both are secondary alcohols, so we can't use a Lucas reagent to identify tertiary alcohols and secondary alcohols apart, because both of these are secondary alcohols. If one was a tertiary alcohol, we could have used Lucas reagent. But we can get to that point by dehydrating these, actually removing the OH group and forming a double bond by adding KOH in alcoholic medium. Or ethanolic KOH. So then what happens? Then you can see the OH will get removed and a double bond would be formed. When it comes to the first compound that we have over here, we can see the formation of this particular compound. When it comes to the second compound, you'll be forming a double bond over here. Right. So after getting to this point, it is just a matter of adding one more OH group again. And we can use dilute sulfuric acid to do so. We can use dilute H2SO4. And you know, when it comes to the addition of an OH group through dilute sulfuric acid, it normally takes place through the formation of a carbocation. First, one of the hydrogens or double bond will be attacked by a water molecule, and that will create a carbocation. So students, since this reaction is taking place through a carbocation, the carbon that is containing the positive charge should be stable. So when it comes to these two compounds, or when it comes to A and B's products, where do you think when this particular double bond is being broken, so basically a water molecule will come its way, and I will draw it in different colors so that you can see the difference very clearly. When this double bond is given here, if the hydrogen attached to the carbon number, let's say this is carbon number 1, 2, and 3. If the hydrogen attaches to carbon number 3, carbon number 2 will get a positive charge. So there's only two alkyl groups, one CH3 and one CH2CH3 group pushing electrons towards it, which is not going to be like equal two groups that are pushing electrons towards it. So therefore you won't see much of a reduction in the stability, or much of a increase in the stability of the carbon with the positive charge. But if this hydrogen gets attached to carbon number 2, at that point the positive charge is going to be present on carbon number 3. There are two CH2CH3 groups pushing electrons towards it due to the electron releasing nature of the alkyl groups, which actually helps to stabilize this carbocation or the positive charge on the third carbon a bit more. So therefore the hydrogen attaches to the second carbon and the OH attaches to the third carbon, forming this CH3 CH2, OH, which is a secondary alcohol. When it comes to the third, when it comes to the B product, or product formed from compound B, when a water molecule is reacting with this particular alkene, if the hydrogen attaches to this carbon, the carbon adjacent to it will get a positive charge. And at that point, it's just a secondary carbocation. That is a CH3 group, an alkyl group pushing electrons towards it. Again, the stability won't be that high. Right? This is just a secondary carbocation. Only two alkyl groups are releasing electrons towards the positively charged carbon. But if the hydrogen gets attached here, then you can see the positive charge lies on this particular carbon, the second carbon, which is a tertiary, which is going to be forming a tertiary carbocation. So when it comes to forming a tertiary carbocation, that will be more stable. Therefore, what you form is this particular compound, CH3, CH3, and the OH will attach to this carbon, CH2, CH3. Now we have formed a secondary alcohol and a tertiary alcohol. Secondary and a tertiary alcohol can be separated by the addition of Lucas reagent. So at this point, if you add anhydrous zinc chloride and concentrated hydrochloric acid, which is the Lucas reagent, you'll be forming a instant turbidity here. Instant turbidity or instant cloudy nature will be observed in the medium. When it comes to secondary alcohols take about 5 to 10 minutes to give a turbidity. So therefore, secondary alcohols can be identified separately with the use of Lucas reagent. So we can simplify this by writing Lucas reagent So if you add the Lucas reagent, an instant turbidity will be formed when it comes to tertiary alcohols. That is because this OH group will be replaced by a Cl group forming an alkyl halide. So those are not soluble in water. Due to this fact, you will see a layer separation, and before that you actually see an instant turbidity formed in the reaction mixture. Right, students, so now with that, you will actually not see an instant turbidity here. It will take about, let's say, about 5 to 10 minutes before you see a turbidity in secondary alcohols. Now students, let's take a look at a summary of what we did here. Now they're asking us to identify A and B separately with a single chemical reaction. We know we can do that by the iodoform test, but since the iodoform test is out of the syllabus, we were looking at different tests that can be used to separately identify them. So when it comes to the different or second or alternative method, we saw we can first take these ketones and react them with lithium aluminium hydride, which is a reducing agent. We reduce them into their alcohols, and then when we are reacting an alcohol with aluminium oxide and heating it, we can remove the this oxygen and create a double bond. Sorry students, in this case you can see I have written the incorrect reagent here, not potassium hydroxide in ethanol that is normally used, or ethanolic potassium hydroxide is used to create a double bond or to carry out elimination reaction when it comes to alkyl halides. Over here, it should be Al2O3, not the alcoholic or ethanolic potassium hydroxide. So please do make that correction. So when you use aluminium oxide and heat it along with these compounds, you will form a double bond, and after forming the double bond, if you react it with dilute sulfuric acid, you get to form a secondary alcohol and a tertiary alcohol, which we identified with the use of Lucas reagent. So since iodoform test is not in the syllabus anymore, we can actually use these tests to identify between these two compounds. Now let's move on to the next slide. How can you identify A and C separately with a single chemical reaction? A and C. So we have A and C. A is a ketone, C is a aldehyde. A is a ketone, C is a aldehyde. So when it comes to aldehydes and ketones, how do you identify them separately? So we quickly write the structures here. This is A. When it comes to C, that is, we have C here. So aldehydes and ketones can easily be identified separately by a simple reaction like Tollens reagent or maybe Fehling's, right? So we can actually take Tollens reagent because that gives us a really good reaction. So you can write, if you use Tollens reagent, you can see the formation of a silver mirror here. A silver mirror formed when it comes to this particular reaction. And if you do the same reaction to the ketone, no change. You will not necessarily see a change here. You won't see the formation of a silver mirror. So therefore, you can use this reaction to identify between aldehydes and ketones. You can use other reactions as well. Acidified potassium permanganate can be used. When you use acidified potassium permanganate, what happens? Ketones will not get oxidized, but aldehydes can get oxidized to form the carboxylic acid. So then what happens? The color of acidified potassium permanganate, which is purple, will disappear as it forms Mn2+. KMnO4 goes to Mn2+. So because of that, you can actually identify between these two compounds. Potassium dichromate, another oxidizing agent. Oxidizing agents can only oxidize aldehydes. So potassium dichromate can oxidize aldehyde and go from orange color to a green color. Again, another test to identify between these two. Fehling's. When it comes to Fehling's reagent is a dark blue color reagent. So when you react these two, we actually take a small amount of Fehling's and these separate compounds into two separate test tubes. And when you mix Fehling's with them and heat it in a water bath, you will see in about 5 minutes, the aldehyde will form a brick red precipitate. Because in the presence of Fehling's, aldehydes can get oxidized. But what about ketones? Ketones will not. Ketones will not get oxidized in the presence of Fehling's. So therefore, you will not see the formation of brick red precipitate. This is a good time to remember. Fehling's will only show a brick red precipitate with aliphatic aldehydes. With aromatic aldehydes and ketones, you will not see a precipitate being formed. So does with aliphatic ketones. With aliphatic ketones also, Fehling's will not show a precipitate. Let's say when A, B and C is reacted separately with CH3MgI and added with water, what products are formed? Give their structure. So students, basically they are asking us about Grignard's reagent. when you are reacting each of these reactants, carbonyl compounds, with the Greenhouse reagent and added with water, what are the products that are formed? So let's first take a look at what type of reactions will take when you take a carbonyl group and react a greenhouse reagent like CH3MgI with the carbonyl group. It will be easier for us to then move on to the answer. So when you have a carbonyl group like this, and when you react it with CH3MgI, so CH3MgI has this situation going on. So we can see the CH3 group will attack this carbon as carbon-oxygen bond is polarized in a way that oxygen has a delta negative charge, carbon has a delta positive charge, and carbon is electron deficient at this point, or has a lower electron density, which is making it more inclined to getting attacked by a nucleophile. At that point, the carbon-oxygen bond, will break and will form this. Now, as MgI is going to be positively charged, MgI is going to be connected to this negatively charged oxygen. When you react this with water, you will be forming an OH group instead of OMgI, and the attached CH3 group remains. So students, the carbonyl compound turns into a OH and a CH3 group, or the carbon actually goes from being a carbon into a carbon that is attached to an OH and a CH3 group when you react any carbon compound with CH3NgI. So the answer over here to our question is, when it comes to the first compound, we'll go compound by compound. When it comes to the first compound, it will form CH3, CH2, OH here. Instead of like carbon, we have an OH here now, and another CH3 group attached here, and CH2, CH3. That's the first compound, or the product formed from A. Let's move on to the product formed from B. When it comes to the product formed from B, you can see we'll draw it in a different color since these are somewhat close to one another. We have OH and CH3 group over here and another CH3. So that is the second compound when you react CH3MgI and then reacted it with water. And afterwards, after this, we have the compound C. We'll go back to red. So compound C forms CH3, CH, CH2, and the carbon compound now has OH group. The hydrogen that was always there is still here. Apart from that, you will have a CH3 group here. Actually, to make it easier for you to understand the actual carbon chain, we will draw the CH3 here. We'll draw the CH3 here and the hydrogen here. Now students, it is just a matter of naming these compounds. The first compound can be named the following way. We have to name it in such a way that the OH group gets a smaller number. As you can see, since the OH group is connected to the carbon in the middle, if you started to number it from the left hand side or the right hand side, it would not make a difference. So we can start numbering it from the left hand side or the right hand side according to your preference. 1, 2, 3, 4 and 5. So the OH group is present on the third carbon, and there's an alkyl group, CH3 group, which is a methyl group, present on the third carbon as well. And the overall length of the carbon chain is 5 carbon atoms long. So the name of this would go as 3-methyl. Since they have 5 carbons, this is containing pent, and the OH is present on the third carbon, 3-ol. 3-methyl pentan, 3-ol is the name. When it comes to the next compound made from B, you can see the main carbon chain. You have to identify the main carbon chain. Main carbon chain would be this. And when you're numbering it, you have to make sure that you number it in such a way that it will have the lowest number or OH group or carbon that is connected to the OH group has a very low number. So we can start numbering it like this: carbon number 1, carbon number 2, 3 and 4. So on the second carbon, you have the OH group and a methyl group, and on the third carbon, you have another methyl group. So you can name this as 2, 3, because on the second and the third carbons, you have a methyl group, dimethyl. 2, 3, dimethyl butane. On the second carbon, you have an OH, which is going to give you 2-ol part of the name. So 2, 3 dimethyl butane 2-ol. 2, 3 dimethyl butane 2-ol. Then we finally move on to the last compound. In this compound, you can see we have a bit of a lengthier carbon chain. This is the main carbon chain, and that carbon chain contains 5 carbon atoms. 1, 2, 3, 4, 5. And when you're numbering it, make sure to number it in a way that the oxygen or OH group connected to carbon gets the smallest number, or carbon connected to the OH group gets the smallest number. So in this case, you have the following name, and there's a methyl group, CH3 group present here. So the answer would be 4-methyl pentan 2-ol. 4-methyl pentan 2-ol. So these are the names of the compounds that we have. When you're reacting each of these A, B and C compounds with CH3MgI, greenhouse reagent, and adding water, you get to these compounds. So answers are 3-methyl pentan 3-ol, 2, 3 dimethyl butane 2-ol, and 4-methyl pentan 2-ol. With that, we'll move on to the next question. How can you separately identify the products formed from A and C in reaction mentioned above? So when it comes to the product formed from A, it is a tertiary alcohol. So I will answer this question here itself because it will be easier. When it comes to the product formed from A, what you see here is a tertiary alcohol. And what you have here, product formed from C, is a secondary alcohol. So tertiary and secondary alcohols can be identified with Lucas reagent. So if you add Lucas reagent here, what do you get? You will get an instant turbidity, right? Instant. Instant turbidity when it comes to tertiary alcohols. When it comes to secondary alcohols, it will take 5 to 10 minutes. We'll write so when it comes to addition of Lucas reagent, you can see the OH group is going to be replaced by a Cl group. We will form alkyl halides. So these are not very soluble in water. Because of that, they will create a cloudy nature in the reaction mixture. So when it comes to tertiary alcohols, this cloudy nature will appear really fast as soon as you include, or as soon as you react the tertiary alcohol with Lucas reagent. You will see a turbidity. When it comes to secondary alcohols, it will take some time. When it comes to primary alcohols, it will take quite a lot of time for it to give a turbidity. It will take way longer than 10 minutes. So from this observation, we can separately identify product from A and product from C. So we have identified. How do we identify it? By the addition of Lucas reagent. We can use Lucas reagent to identify it. Now we move on to the third question. In the third question, they ask, an organic compound named B has the molecular formula C5H8O. B is a ketone, very, very important. B is a ketone, but it is not a cyclic compound. Draw the structures of the isomers of B. B is a ketone, it is not a cyclic compound. We have to draw the structures of B. So it has 5 carbons. Let's start with that. Let's start with 5 carbons. One. All right, we actually can start including hydrogen itself. It will be easier. CH3, CH2, CH3. I have already drawn 3 carbons. CH2 here. And then I can move on to writing the carbonyl-carbon. Since this is a ketone, I can't keep the carbonyl-carbon in a terminal position. If I put the carbonyl-carbon in a terminal position, it becomes an aldehyde. So I can't necessarily keep this carbonyl-carbon over here. This is the structure that you will first start to draw. But immediately you will notice that this can't be one of the answers because this has more hydrogen than what the formula has mentioned. The formula has mentioned the number of hydrogens is supposed to be 8. Over here, we have 10. We have 10, so we can immediately move on to removing some hydrogens by including a double bond. So we'll include a double bond over here. Now our problem is fixed. Now we can see there are only 8 hydrogens. There are only 8 hydrogens here. So after this, they ask us to write down all of the structures of isomers, or all the isomers of B. So this could be one of the isomers where you have the double bond over here, and since one of the carbons connected to the double bond has two similar groups, we can't draw cis-trans isomers here. So while keeping that in mind, you can move on to the next type of compound that you find here, which is this. You can bring the carbonyl compound over here. When you do that, you get this CH2, CH, C double bonded O, CH2, CH3. This is one isomer. We can move on to a few other isomers like this. Can I include the carbon-carbon double bond? Can I include the carbon-carbon double bond over here? No. At that point, since this can actually have altogether 5 carbons, 1, 2, 3, 4, 5. Since I have not drawn 5 carbons, I actually can include, I can write this over here. Right, students. So at this point, you can see we have kept the first, when it comes to the first compound, the double bond was present between the first and second carbon, and then while keeping it in one place, we have brought in the ketone group or carbonyl group to closer to the double bond. That was the second isomer, and afterwards we started moving the double bond. So when we started moving the double bond to the second position, we are starting to see geometrical isomerism. So when you draw this particular isomer, keep in mind it has 2 isomers within it, cis and the trans isomer. So this can have 2 isomers. You will have the cis isomer and the trans isomer. And over here, you can have another isomer here. Right, students. So you can see when it comes to this particular compound, there are both cis and trans isomers. There are both cis and trans isomers present here. So this is actually the trans isomer. We have the cis isomer here. Now with that, we actually have drawn a few isomers for this particular compound. There are no other possible isomers that we can draw for this compound, but let's take a look at if there are any other isomers that we can draw. No, we don't have any other isomers that can be drawn for this compound. So therefore, we'll be moving on to the next question. So if you want to have all of the isomers in a single picture, you can see it here. Students, let's take a look at the 4th question. How would you separately identify the compounds that are given below in each pair of compounds? So you can see, students, we have but1-ene and but2-ene. Both of them contain a double bond. So you can't usually use your usual test to identify double bonds to separately identify these two. For example, if you added bromine water to see if bromine water gets decolorized, you would note both of these will decolorize bromine water. Both of them have a double bond. So we can't separately identify these two compounds with tests that are designed to identify double bonds. So we have to convert them into something else before identifying these two compounds separately. Right, so let's take these two compounds and we'll react them with bromine water or bromine. You will get the following products: CH3, CH2, CH, CH2, but there will be bromine added across the double bond. Over here, you will have CH3, CH, CH, CH3, and again across the double bond there will be bromine added. So after the addition of bromine, you can move on to adding ethanolic KOH. Now, when you're adding ethanolic KOH, you would note that there will be a double bond, or actually a triple bond formed between the first and the second carbon here, and second and the third carbon here. So you'll be forming these compounds. And over here, you will have the triple bond between second and the third carbon. Now we have an alkyne where the alkyne group is present in a terminal position. So what do you know about alkynes or terminal alkynes? When you have terminal hydrogens like this, what can they do? They can react, or they actually show acidic properties, and they can react with sodium. They can react with ammonia and silver nitrate, or ammonia and cuprous chloride. So we can actually, from this point, identify these two separately. So if you add to both of them, if you add ammonia and silver nitrate, this particular alkyne, which is butene or 1-butene, can form a white color precipitate with ammonia and silver nitrate. Can this product do that? No. So there will be no PPT or no precipitate, because the alkyne or the carbon-carbon triple bond is present in it's not present in a terminal position. So these are terminal alkynes, these are internal alkynes. When it comes to terminal alkynes, the carbon-carbon triple bond is present in a terminal position. When it comes to the second product that we have here, it is not present in a terminal position, so you can't react, or they can't react with ammonia and silver nitrate and produce white color precipitate. Another test that can be done at this point is the addition of, you can add ammonia and CO2, Cl2, cuprous chloride. You will see the formation of a brick red precipitate. You will see the formation of a brick red precipitate, CH3, CH2, which is this particular product. I will separate these two The product that we see over here is going to be brick red in color. But do you see the same observation over here? If you added ammonia and copper cuprous chloride, if you add ammonia and Cu2Cl2, do you see the formation of a precipitate? No. So we can say no change or no precipitate. No precipitate will be formed. Right, students? So that is how you can identify these two compounds separately. Now let's move on to the next question. We have, how do you separately identify the compounds that are given below in each pair of compounds? We have aldehyde or benzaldehyde, and then we have another benzaldehyde group, but you have a ketone connected to the benzene ring. So how do you separately identify these two? Can we use Brady's reagent? No. Both of them are, and plus aldehydes and ketones, both usually answer to Brady's reagent. We can't use it. Can we use Fehling's solution? Fehling's will not answer to aromatic aldehydes. What about the use of Tollens reagent? Both will answer to Tollens. But still, there's a little bit of an advantage to that. That is, when Tollens is reacted with these, only the aldehyde group gets oxidized. The ketone will not get oxidized because Tollens reagent is not going to be strong enough to oxidize this ketone group that we have here. If you had used something like acidified potassium dichromate, again, you can't separately identify these two, but at the same time, acidified potassium permanganate would have converted this group into a carboxylic acid group. When it comes to the second compound, both of these groups, both of them would have been converted into carboxylic acid groups. So you can't use acidified potassium permanganate as well, because even after the very first test, you can't use the products that are formed to carry out another test. So therefore, students, we can use Tollens reagent. We can use Tollens reagent. So we are not keen on the very first observation. Very first observation when it comes to Tollens is the formation of silver mirror. So when it comes to adding Tollens, you will see the formation of silver mirror. But apart from the silver mirror formation, the reaction mixture that is going to be remaining, or actually the products mixture that is going to be remaining, contains these products. When it comes to the very first compound, after reacting it with Tollens reagent, you are going to have COO minus formed, or we can say a carboxylic acid anion is going to be there. And when it comes to the second compound, you're going to have benzoate anion, but in this case, you can see in the meta position, you have a ketone. Does the ketone get affected by Tollens reagent? No. Ketone will remain intact. So therefore, students, after the very first test, that's why I said we are not very keen on the silver mirror, because both of these instances you will form the silver mirror. After the very first test, you can carry out another test. In this test, you can use Brady's reagent, 2,4-DNP. Brady's, or in other words, 2,4-DNP can be used, 2,4-dinitrophenylhydrazine. So if you add 2,4-DNP, you will see a yellow orange precipitate. You will see a yellow orange precipitate. But would you see the same over here? If you add 2,4-DNP, you will see no change. You will see no change. When it comes to this product, benzoate ions, you would not see a reaction with 2,4-DNP. So this is how you would identify these two compounds separately. With that, students, we come to an end of the discussions of the questions that we have done for this particular experiment. We have seen the reactions in the lab. Now we have gone through the theory parts again and discussed questions. I hope this elevates your knowledge about this particular theory part. That will be all for this experiment. I will see you guys again in the next experiment.